Look up at the stars tonight, really look, and let yourself wonder for a moment. Among those countless pinpricks of light, there are worlds so strange, so breathtakingly different from our own, that they seem ripped from the pages of science fiction. Yet these places are real. Astronomers have discovered thousands of exoplanets' worlds orbiting distant suns, and among them, 40 stand out as the most enigmatic, the most tantalizing, the most likely to harbor something extraordinary. Life, not the little green men of Hollywood, but perhaps microbes thriving in the steam of a volcanic moon, or organisms dancing in the eternal twilight of a tidally locked planet. The mere possibility sends chills down the spine. Think about what it would mean to find life, any life, beyond Earth. It would shatter our cosmic loneliness, rewriting the story of humanity's place in the universe. These 40 worlds aren't just scientific curiosities. They're keys to the biggest question we've ever asked. Are we alone? Some are hellish landscapes where it rains molten rock, others frozen spheres hiding vast oceans beneath their icy shells. A few orbit in the perfect sweet spot, not too hot, not too cold, where liquid water could pool on their surfaces, just like home. But here's the twist. Life might not need, just like home, to survive. It could flourish in ways we haven't even imagined. That's the thrill of this hunt. Every new discovery stretches the boundaries of what we consider possible. Could there be silicon-based life forms basking in the glow of a red dwarf star? Could entire ecosystems thrive in the crushing depths of a super-Earth's atmosphere? We're on the brink of finding out. In this journey, we'll explore these 40 mysterious worlds one by one, their scorching deserts, their howling winds, their silent, dark oceans, and uncover why scientists believe they might be the best candidates for life beyond our solar system. So buckle up. The universe is about to get a whole lot stranger. For centuries, humans could only dream of worlds beyond our solar system, planets circling distant suns, hidden in the vast darkness of space. Today, thanks to revolutionary tools like the Kepler Space Telescope and TESS, we've moved from speculation to staggering reality. Over 5,000 exoplanets confirmed, each a testament to how crowded and diverse our galaxy truly is. But here's the catch: not all these worlds are created equal. The hunt for habitability isn't just about finding planets, it's about finding the right ones. Take the Goldilocks Zone, for example. This sweet spot around a star where temperatures are just right for liquid water to exist has long been our guiding light. Too close and oceans boil away, too far and everything freezes solid. But habitability is far more nuanced than distance alone. A planet's atmosphere acts like a cosmic blanket, trapping heat or scattering it into space. A thick carbon dioxide shroud could turn a chilly world into a temperate paradise, while a thin or non-existent atmosphere might leave even a Goldilocks planet barren. Then there's geology. A planet with a molten core could generate a protective magnetic field, shielding life from deadly stellar radiation. Volcanic activity might recycle nutrients, while tectonic shifts could regulate climate over eons. And let's not forget water, the universal solvent for life as we know it. Some exoplanets may harbor vast subsurface oceans, hidden beneath miles of ice, where hydrothermal vents could fuel entire ecosystems untouched by sunlight. But here's what's truly exciting. Life might not need Earth-like conditions at all. Imagine organisms thriving in the methane lakes of a freezing world, or microbes drawing energy from chemical reactions deep in a planet's crust. Every discovery challenges our assumptions, forcing us to rethink what habitable even means. That's why these 40 enigmatic worlds are so thrilling. They're not just dots on a star map. They're invitations to rewrite the rules of biology itself. Proxima Centauri b isn't just another exoplanet, it's our cosmic next-door neighbor, a mere 4.2 light-years from Earth. Imagine stepping outside on a clear night and spotting Alpha Centauri, the closest star system to our Sun. That faint red dot, that's Proxima Centauri, and circling it is a world that could rewrite everything we know about life in the universe. What makes this rocky planet so special? For starters, it's nestled snugly in its star's habitable zone, where temperatures might allow liquid water to exist. But here's the catch: Proxima Centauri b is tidally locked, meaning one side basks in eternal daylight while the other is frozen in endless night. Yet life, if it exists there, might thrive in the twilight, the narrow band where day and night meet. Picture a landscape where the sun never rises or sets, hanging motionless on the horizon, casting perpetual amber hues over lakes or oceans that never boil away or freeze solid. Recent research hints at something even more surprising. Despite Proxima Centauri's violent flares, which bombard the planet with radiation, a thin atmosphere could act as a shield, scattering just enough energy to protect fragile ecosystems. Scientists have even speculated about subsurface oceans, hidden beneath icy crusts, where life could evade the harsh surface conditions entirely. But the real question isn't just whether Proxima Centauri b could harbor life, it's whether we'll ever know for sure. This world is so close that future telescopes might analyze its atmosphere for biosignatures like oxygen or methane that betray the presence of living things. Imagine the implications: alien organisms practically in our stellar backyard. Of course, red dwarf systems come with challenges. Their habitable zones are tight, exposing planets to extreme tidal forces and stellar winds. Yet if life can endure here, it suggests the galaxy might be far more hospitable than we ever dreamed. Proxima Centauri b isn't just a scientific target, it's a beacon, reminding us that the search for life isn't confined to distant star systems. The answer could be closer than we think. Picture a solar system where you could watch 6 other worlds hanging in the sky, some appearing larger than our moon, not as distant dots, but as fully realized landscapes swirling with clouds or gleaming with ice. This isn't science fiction. It's the everyday reality for any hypothetical inhabitants of the Trappist-1 system, a cosmic jewel box just 40 light-years away. At its heart, a dim red dwarf star pulses quietly, barely larger than Jupiter, yet it hosts 7 rocky planets, 3 of which orbit in that precious habitable zone where water could flow freely. What makes this system extraordinary isn't just the number of Earth-sized worlds, but their intimacy. These planets are packed so tightly that a year on the innermost one lasts just a day and a half, while even the outermost completes its orbit in under 3 weeks. Such proximity raises wild possibilities. On Trappist-1e or F, the most promising candidates for habitability, neighboring planets would loom large enough to reveal surface details with the naked eye. Imagine standing on a misty shoreline, watching twin crescent worlds rise over an alien ocean, their silhouettes etched by mountain ranges or vast storms. But this cosmic closeness also fuels scientific debate. Could life hitchhike between these worlds? On Earth, microbes survive the harshness of space, clinging to meteorites. In Trappist-1 cozy arrangement, a violent impact on one planet might scatter debris easily captured by another, seeding life across the system. Yet challenges lurk. Red dwarfs like Trappist-1 are notorious for their tantrums, flinging out radiation bursts that could strip atmospheres over time. But here's the twist: these planets might be saved by their own tight-knit dance. Some researchers suggest their gravitational tugs could generate internal heat through tidal friction, keeping subsurface oceans liquid even without sunlight. Others point to potential atmospheres thick with carbon dioxide, acting like insulating blankets. The real excitement lies in what's next. Trappist-1 planets transit their star frequently, giving telescopes like JWST countless opportunities to analyze their atmospheres for signs of water, methane, or even oxygen. Detecting these biosignatures wouldn't just hint at life, it could reveal a network of habitable worlds right in our galactic neighborhood. If just one of these 7 holds life, the implications are staggering. We might be looking at a system where biology isn't the exception, but the rule. Kepler-186f wasn't just another exoplanet discovery, it was a revelation. When astronomers confirmed its existence in 2014, it marked a turning point in our cosmic search. For the first time, we had proof, an Earth-sized world, perched perfectly in its star's habitable zone, where liquid water could pool on its surface. Picture standing on this distant shore, gazing up at a sun that glows dimmer and redder than ours, casting everything in perpetual sunset tones. Plants, if they exist here, might evolve to photosynthesize with infrared light, painting the landscape in deep purples and blacks instead of Earth's familiar greens. What makes Kepler-186f so remarkable isn't just its size or location, it's the tantalizing possibility of stability. Unlike many exoplanets orbiting turbulent red dwarfs, this world circles its star at a safer distance, potentially avoiding the brutal tidal locking and radiation flares that plague closer-in planets. Some models suggest it could even have seasons, its axial tilt creating rhythmic climate changes akin to Earth's. But here's the twist. Its star, Kepler-186, is far cooler than our Sun, meaning this planet's year lasts just 130 Earth days. A shorter orbit might mean more extreme temperature shifts unless a thick atmosphere smooths them out, acting like a planetary thermostat. The discovery shattered old assumptions. Before Kepler-186f, we'd found gas giants in habitable zones or rocky worlds baking too close to their stars. This was different, a place where the ingredients for life as we know it could plausibly mix. It also raised profound questions. Could photosynthesis work under crimson starlight? Would life adapt to longer nights or lower energy input? The answers might rewrite biology itself. Yet mysteries linger. Without direct images, we can't yet know if Kepler-186f has oceans or continents. Its gravity, slightly stronger than Earth's, could mean towering mountains or deep basins. And while its star's calm nature boosts its habitability prospects, we've detected no signs of an atmosphere yet. Future telescopes could change that, analyzing starlight filtering through its skies for hints of water vapor or oxygen. Kepler-186f's greatest legacy isn't just about one world. It proved that planets like ours aren't cosmic accidents, they're out there, waiting to be found. Every new telescope now scans the heavens with renewed purpose, because if an Earth twin exists 500 light-years away, how many more might be closer? This single discovery didn't just expand our atlas of exoplanets, it redefined what's possible in the universe. LHS 1140b isn't just another exoplanet, it's a cosmic heavyweight, a super-Earth with secrets that could redefine our understanding of habitable worlds. Clocking in at 40% larger than our own planet, this dense, rocky giant orbits a red dwarf star so calm and steady, it's practically a stellar Zen master. While many red dwarfs unleash deadly flares, LHS 1140b's parent star is unusually tranquil, offering a rare gift, stability. That's a game changer in the search for life. But here's where it gets even more intriguing. This planet's sheer mass suggests it could be holding onto something precious, a thick, protective atmosphere. Picture an alien sky dense with nitrogen or carbon dioxide, scattering radiation and locking in warmth like a planetary greenhouse. Now, let's talk about the real showstopper, water. Recent models paint a jaw-dropping scenario. LHS 1140b might be a true water world, its entire surface submerged beneath a global ocean. Imagine an endless, dark sea stretching to the horizon, with pressures so intense that ice forms not from cold, but from crushing depth, creating exotic layers of hot ice near the core. Yet, even in these extreme conditions, life could find a way. Hydrothermal vents, like those fueling Earth's deep-sea ecosystems, might dot the ocean floor, spewing minerals into the abyss. Microbes, or something far stranger, could thrive in these alien oases, utterly divorced from sunlight. The next chapter of this mystery lies in the planet's atmosphere. Upcoming telescopes will scour starlight filtering through its skies, hunting for the telltale fingerprints of water vapor or oxygen. Detecting either would be a seismic discovery, but there's a catch. This world's gravity is so strong that landing there would feel like carrying double your weight. Mountains, if they exist, might be stunted by the relentless pull, while any waves on that hypothetical ocean would move in slow motion. What makes LHS 1140b so compelling isn't just its potential to host life, it's the way it challenges our assumptions. A planet this massive shouldn't be this promising, yet here it is, defying expectations. If future observations confirm its ocean, it could leap to the top of humanity's interstellar travel wish list. After all, where there's water, there's hope, and this super-Earth might be holding oceans of it. K2-18b shatters every expectation we've ever had about habitable worlds. This isn't a planet that plays by Earth's rules, it's a swirling, steamy enigma, a place where the very definition of ocean takes on a new meaning. When astronomers announced they'd detected water vapor in its atmosphere back in 2019, the scientific community reeled. Here was a world twice Earth size, 8 times its mass, and drenched in a hydrogen-rich atmosphere so thick it creates pressures that would crush a submarine. Yet beneath that suffocating blanket, something extraordinary might be happening. A global ocean, not of liquid water as we know it, but a supercritical fluid where the line between liquid and gas blurs into oblivion. What makes K2-18b so revolutionary is its classification as a Hycean world, a term coined just years ago to describe these hot, water-rich planets with hydrogen skies. Picture an endless twilight sea, heated not by sunlight but by the planet's own internal warmth and the greenhouse effect of its atmosphere. Surface temperatures could soar past 200 degrees Fahrenheit, yet in the abyssal depths where pressure stabilizes the chaos above, pockets of cooler water might exist. And where there's water, there's potential. Earth's extremophiles organisms thriving in boiling hydrothermal vents or toxic acidity prove life can flourish in the unlikeliest places. Could K2-18b's depths harbor similar survivors, metabolizing hydrogen or organic molecules swirling in those alien seas? The real magic lies in the chemistry. Hydrogen atmospheres are simpler to analyze than Earth, like nitrogen-oxygen mixes, making biosignatures easier to spot. Imagine methane or dimethyl sulfide gases often linked to biological activity, lingering in those steamy skies. Future telescopes like the James Webb Space Telescope could soon give us answers, dissecting the light filtering through K2-18b's atmosphere with unprecedented precision. But here's the twist: this world orbits a red dwarf, a star type notorious for violent flares. Normally, such radiation would strip away atmospheres, but K2-18b's massive size and gravity might act like a cosmic shield, holding its gases close. That resilience suggests Hycean planets could be common, hiding in plain sight around dim stars across the galaxy. If life can thrive here, in this pressure cooker of an ocean, then the universe might be far more inventive and far more alive than we ever dared to dream. GJ-1214b isn't a planet, it's a paradox. Imagine a world where the very ground beneath your feet vanishes, replaced by an endless, churning ocean so deep it defies comprehension. This isn't science fiction, it's the reality of this enigmatic super-Earth, a place where the concept of land doesn't exist. What makes GJ-1214b so extraordinary isn't just its lack of surface, it's the sheer strangeness of its water. Here, pressures are so intense that H2O behaves in ways that would seem impossible on Earth, forming exotic states like hot ice, where water molecules lock into crystalline structures despite scorching temperatures, or superfluid water, a frictionless liquid that flows like nothing in our experience. The planet's thick, steamy atmosphere adds another layer of mystery. Unlike Earth's transparent skies, GJ-1214b's shroud is so dense with water vapor that sunlight barely penetrates, casting the oceans below in perpetual twilight. Yet within that gloom, there could be motion colossal currents driven by tidal forces or heat from the planet's core, creating vast, slow-moving whirlpools that span continents. If life exists here, it wouldn't cling to rocks or soil. It would drift, suspended in a global broth, perhaps resembling Earth's plankton, but evolved to thrive in crushing pressures and alien chemistry. But here's the twist. GJ-1214b orbits so close to its dim red dwarf star that a single year lasts just 38 hours. This proximity should make it a broiling wasteland, yet its atmosphere acts like a pressure cooker, trapping heat so efficiently that temperatures might allow liquid water to persist at certain depths. Some scientists speculate about layered oceans, a scalding surface beneath the steam blanket, transitioning to stranger forms of water as you descend, with life huddled in a narrow band of habitability somewhere in between. The real challenge is imagining biology here. Without solid surfaces, organisms might rely on floating colonies or gel-like structures to maintain their form. Energy could come not from sunlight but from chemical reactions in the water itself, or from geothermal vents spewing nutrients into the abyss, and reproduction. It might involve free-floating spores or particles carried by currents, a life cycle utterly divorced from anything on Earth. What GJ-1214b teaches us is that habitability isn't about matching Earth's template, it's about adaptability. A planet like this forces us to rethink the extremes life can endure, and in doing so, expands the horizons of our cosmic search. If something stirs in those dark, pressurized seas, it won't just be a scientific discovery. It'll be a revelation that life isn't a rare fluke. It's a phenomenon as vast and varied as the universe itself. TOI 700d isn't just another exoplanet. It's a cosmic rarity, a world that ticks nearly every box on our habitability checklist. Discovered by NASA test mission in 2020, this Earth-sized gem orbits a quiet red dwarf star, basking in the gentle glow of its habitable zone. What sets it apart isn't just its size or location, it's the extraordinary stability of its environment. While most red dwarfs unleash violent flares capable of stripping away atmospheres, TOI 700 is a celestial pacifist, emitting barely a flicker of disruptive radiation. That tranquility could be the key to preserving something precious, liquid water. Early climate models paint a tantalizing picture. TOI 700d's 37-day year might sound brisk compared to Earth's, but its orbital dance keeps temperatures just right, not too hot to boil its oceans away, not too cold to freeze them solid. Some simulations suggest it could even sport sprawling cloud cover, reflecting just enough starlight to maintain a temperate climate. Picture standing on its surface beneath a salmon-colored sky with the star hanging large but dim like a perpetual sunset. The air might be thick with nitrogen or carbon dioxide, creating a greenhouse effect that blankets the planet in cozy warmth. But here's what really excites scientists. TOI 700d is a prime candidate for atmospheric analysis. Its size and position make it ideal for telescopes like JWST to probe its skies for water vapor, oxygen, or methane, gases that could hint at biological activity. Imagine detecting a whiff of oxygen alongside methane, a combination that on Earth almost always signals life. That's the dream scenario. Yet even if its atmosphere proves barren, TOI 700d offers something equally valuable, a benchmark. It's a controlled experiment in habitability, a chance to study how Earth-like worlds evolve around the most common stars in the galaxy. The planet's potential doesn't stop at its atmosphere. Its rotation remains a mystery. Is it tidally locked with one side forever facing its star? Or does it spin just enough to create day-night cycles? A slow rotation could lead to dramatic weather patterns, with supersonic winds redistributing heat across the globe. Or perhaps it has a molten core, generating a magnetic field to shield its surface from cosmic rays. Every unanswered question makes TOI 700d more compelling. What makes this world so special isn't just its science, it's the hope it represents. In a universe where most habitable zone planets orbit unruly stars, TOI 700d is a quiet rebel, proving that peaceful red dwarfs can offer safe harbor for life. Future missions will scrutinize its secrets, but for now, it stands as a beacon, reminding us that Earth's twin might be out there, waiting to be found. The search isn't just about discovering life, it's about discovering possibilities, and TOI 700d is overflowing with them. Kepler-22b isn't just another exoplanet, it's a mirror held up to Earth across the vastness of space, showing us what our own world might become. Orbiting a star nearly identical to our Sun, this so-called Earth 2.0 exists in a cosmic sweet spot where the rhythm of its seasons and the length of its year feel hauntingly familiar. Picture a place where a calendar page turns just 20 days slower than ours, where sunlight filters through an atmosphere that could be rich with nitrogen and oxygen, and where towering volcanoes might still rumble across its surface after 6 billion years of activity. That staggering age is what sets Kepler-452b apart. It's had 1.5 times longer than Earth to nurture life, evolve ecosystems, and perhaps even birth civilizations. The planet's size, 60% larger than Earth, paints a dramatic picture. Gravity here would feel stronger, pulling down on hypothetical mountain ranges with enough force to compress them into sprawling plateaus. Yet that extra mass could also mean a more robust magnetic field, shielding the surface from cosmic radiation and preserving a thick atmosphere. Active volcanism, hinted at by its likely molten core, might recycle nutrients and regulate climate over eons, just as Earth's volcanoes do. But here's the twist. All that geological activity could also mean frequent upheaval, with continents shifting and oceans reforming on scales that dwarf our own planet's restless movements. What truly fires the imagination is the question of time. 6 billion years is more than enough for life to have climbed from simple cells to staggering complexity, if it ever began at all. On Earth, it took just half that time for microbes to evolve into spacefaring humans. What might have emerged on a world with an extra 3 billion years of evolutionary runway? Perhaps intelligence flourished there long before Earth's first fish crawled onto land, or maybe life never sparked at all, leaving Kepler-452b as a lush but silent Eden. The star it circles adds another layer of intrigue. Unlike the red dwarfs dominating the exoplanet catalog, Kepler-452b's Sun is a G-type star, nearly a twin to our own. That means its light, the same golden-white hue we know, could power photosynthesis in ways alien plants might recognize. But there's a catch. This older sun is also brighter, warming the planet's surface over millennia. If Kepler-452b once had Earth-like conditions, it might now be entering a runaway greenhouse phase, its oceans slowly boiling away under the star's increasing glow. Or perhaps its life adapted, retreating to polar refuges or evolving heat-resistant biochemistry. Future telescopes could settle these mysteries by analyzing the planet's atmosphere for biosignatures, oxygen, methane, or even industrial pollutants hinting at advanced civilizations. But for now, Kepler-452b stands as a profound thought experiment, a glimpse into Earth's distant future and a challenge to our cosmic solitude. If life thrives there, it suggests our galaxy could be teeming with ancient, wiser species. If it doesn't, we're left to wonder why, and whether Earth's vibrant biosphere is the exception, not the rule. Either way, this world reminds us that we're not just searching for life. We're searching for our place in a story billions of years in the making. HD 40307G isn't just another super-Earth. It's a world that defies expectations, spinning through space with a celestial wobble that could make it one of the most dynamic exoplanets we've ever discovered. Clocking in at 8 times Earth's mass, this heavyweight doesn't just occupy its star's habitable zone, it dances through it. What sets it apart is something we often take for granted on our own planet: seasons. Unlike many tidally locked exoplanets frozen in eternal twilight, HD 40307G likely has a tilted axis, meaning its hemispheres would experience rhythmic shifts in temperature and daylight as it orbits its orange dwarf star. Picture a landscape where winter might bring months of dim, crimson-tinged light, while summer bathes entire continents in extended golden hour glow. But here's what makes this planet truly fascinating. Its atmosphere could be a game-changer. Models suggest a shroud of gases thick enough to trap heat like a planetary blanket, redistributing warmth from equator to poles. That means even regions farther from the star's direct rays might avoid freezing into wastelands. Imagine temperate zones where liquid water persists year-round, with weather patterns shifting dramatically as the planet's tilt changes solar exposure. On Earth, seasons drive migrations, hibernation cycles, and evolutionary adaptations, so what might they inspire on a super-Earth? Perhaps organisms with bioluminescent displays to communicate during long winters, or flora that stores energy in massive root systems to survive temperature swings. The sheer scale of HD 40307G adds another layer of intrigue. With stronger gravity, life forms might evolve sturdier structures. Think thick, trunk-like legs to support weight, or low, sprawling vegetation to resist fierce winds. Its higher mass also suggests more volcanic activity, which could pump nutrients into the atmosphere, fueling complex ecosystems. Yet challenges loom. That same gravity might make flight nearly impossible, grounding any potential equivalents to birds or insects unless they develop radically different adaptations, like hydrogen-filled air sacs for buoyancy. What captivates scientists most is how this planet's seasons could create pockets of extreme diversity. Just as Earth's tropics host vastly different life than its tundras, HD 40307G's climate variations might spawn entirely separate biomass within relatively short distances. A single continent could transition from steamy wetlands to frost-resistant forests based on axial tilt alone. And if life thrives here, it would prove that seasonal rhythms, not just stable conditions, can be a catalyst for biological complexity. The next decade of observations could settle the biggest question: Does HD 40307G's atmosphere hold the telltale signs of life, like oxygen or methane cycles that fluctuate with its seasons? Future telescopes might catch the planet mid-tilt, analyzing how its atmospheric chemistry responds to changing sunlight. For now, this super-Earth stands as a reminder that habitability isn't just about location. It's about motion, change, and the beautiful chaos of a world that refuses to stay still. Wolf 1061c isn't just close, it's practically in our cosmic backyard, a mere 14 light-years from Earth. That's near enough that future telescopes might one day map its swirling cloud patterns, if it has any. But don't let the proximity fool you. This world is a study in extremes, caught in a gravitational tug of war that makes Earth's most hostile deserts look tame. Orbiting a dim red dwarf, Wolf 1061c straddles the inner edge of its star's habitable zone like a tightrope walker without a safety net. Dayside temperatures could soar high enough to melt lead, while the nightside plunges into perpetual deep freeze. And if that weren't challenging enough, the planet's likely tidal locking means one half bakes under eternal sunlight, while the other languishes in endless darkness. Yet here's the tantalizing paradox. Even in this thermodynamic nightmare, life might find a way. Earth's own extremophiles organisms thriving in boiling hydrothermal vents or buried miles beneath Antarctic ice prove biology can persist in the unlikeliest corners. On Wolf 1061c, the sweet spot could be the narrow terminator line where day and night meet. Picture a twilight belt where temperatures might hover just right for liquid water, with volcanic heat from the planet's interior supplementing the feeble starlight. Subsurface aquifers could exist too, shielded from the surface extremes by layers of rock and ice, creating hidden oases in the dark. The planet's thick atmosphere, if it has one, might be the deciding factor. A dense carbon dioxide shroud could act like a global heating duct, ferrying warmth from the scorching dayside to the frozen nightside, smoothing out the temperature swings. Wind speeds in such a system would be unimaginable hurricane-force gales howling endlessly across the landscape. But for microbes huddled in deep caves or beneath protective mineral crusts, these currents could distribute vital nutrients, creating a bizarre but viable ecosystem. What makes Wolf 1061c so compelling isn't just its potential for life, it's the way it redefines habitable. This isn't a gentle world of forests and oceans. It's a crucible testing the absolute limits of what biology can endure. If something survives here, it suggests life may not need ideal conditions, just a tiny foothold, a fleeting balance between fire and ice. Future observations will scrutinize its atmosphere for water vapor or chemical imbalances that hint at activity below. But even without definitive proof, Wolf 1061c stands as a monument to life's tenacity, whispering that even in the harshest corners of the galaxy, the universe might still find a way to say yes. Gliese 581g isn't just another exoplanet, it's a cosmic ghost story, a tantalizing what if that continues to haunt the scientific community years after its disputed discovery. When astronomers first spotted its faint signal in 2010, headlines blared that we'd found the first truly Earth-like world beyond our solar system. Dubbed Zarmana's world after the lead researcher's wife, this rocky planet appeared to orbit snugly within its red dwarf star's habitable zone, with surface gravity strong enough to hold an atmosphere and temperatures that might allow liquid water to pool. The implications were staggering until other teams scrutinized the data and declared the planet might not exist at all. The controversy boils down to an astronomical detective story. Gliese 581g's discovery relied on the radial velocity method, watching for subtle wobbles in its star's motion caused by an orbiting planet's gravitational tug. But red dwarfs like Gliese 581 are notoriously fidgety, their surfaces roiling with starspots and flares that can mimic planetary signals. Some researchers argue the planet is just stellar noise, a phantom born from wishful thinking and statistical ambiguity. Others counter that the signal persists across multiple analyzers, its rhythmic pull distinct from random stellar activity. What makes this debate so consequential isn't just about one world, it's about how we interpret the faint whispers of distant planets. If Gliese 581g is real, it suggests habitable worlds could be far more common than we thought, especially around red dwarfs that make up 70% of our galaxy's stars. Its potential size, just 20% larger than Earth, puts it in the sweet spot for rocky composition, while its orbital period of 37 days hints at a climate that might avoid the extremes of tidal locking. The mystery deepens when you consider its neighbors. The Gliese 581 system already hosts at least 4 confirmed planets, some icy, some hellish. If G exists, it could be part of a complex cosmic family, with gravitational interactions shaping its climate over eons. Imagine standing on its surface beneath a crimson sky, with sister worlds hanging like glowing marbles in the twilight. For now, the truth remains suspended between discovery and doubt. Newer instruments like espresso could settle the debate, offering precision measurements that might either resurrect Zarmana's world or finally lay it to rest. But either outcome teaches us something vital about the fragility of data, the hunger for discovery, and the electrifying moment when science brushes against the edge of the unknown. Gliese 581g, real or not, reminds us that every exoplanet hunt is part detective story, part dream, and the line between noise and revelation is thinner than we think. Kepler-22b isn't just another exoplanet, it's a cosmic paradox, a world where the very idea of land might not exist at all. Imagine standing on a spacecraft gazing down at this distant sphere, seeing nothing but an endless, unbroken ocean stretching from pole to pole, its surface shimmering under the light of a star slightly cooler and smaller than our sun. This isn't science fiction. It's the compelling reality of a planet twice Earth's size, with gravity strong enough to crush a submarine like a tin can, yet potentially teeming with life in its abyssal depths. What makes Kepler-22b so extraordinary isn't just the presence of water, it's the sheer scale of it. Earth's deepest trench, the Mariana Trench, plunges 7 miles down. On Kepler-22b, oceans could be hundreds of miles deep, with pressures so intense that water behaves in ways that defy our understanding. Down there, ordinary ice doesn't stand a chance. Instead, the crushing force creates exotic phases like Ice 7, a crystalline form that remains solid even at scorching temperatures. Picture layers of this super-dense ice forming a slushy mantle between the liquid ocean above and the rocky core below, a dynamic barrier where chemistry becomes alien. Yet even in this extreme environment, life might find a foothold. Hydrothermal vents, like those dotting Earth's ocean floors, could spew mineral-rich plumes into the darkness, creating oases of warmth and energy. On our planet, entire ecosystems thrive around these vents, fueled not by sunlight but by chemosynthesis bacteria converting sulfur and methane into food. If similar vents exist on Kepler-22b, they might harbor organisms adapted to pressures that would flatten a human in milliseconds. These creatures could resemble Earth's extremophiles, but with biochemistry twisted by the planet's unique conditions, perhaps using silicon instead of carbon, or relying on dense solvents to navigate their crushing world. The planet's atmosphere adds another layer of mystery. A thick shroud of hydrogen and water vapor could act like a pressure cooker lid, trapping heat and maintaining liquid oceans despite the star's faint glow. Storms might rage across its surface with waves towering hundreds of feet, driven by tidal forces from its tight orbit. A year here lasts just 290 Earth days. But below the chaos, the deep ocean could be eerily still, its currents slowed by the weight of the water above. Kepler-22b's greatest lesson is that habitability isn't about matching Earth's template. A planet like this forces us to rethink the very boundaries of life, proving that oceans, not continents, might be the universe's most common cradles for biology. Future telescopes could scan its atmosphere for signs of methane or dimethyl sulfide, gases often linked to living processes. If they find them, it won't just confirm life exists there, it'll reveal that the galaxy's true marvels aren't the rocky worlds we know, but the endless hidden seas we've yet to explore. Ross 128b isn't just another exoplanet, it's a cosmic sanctuary, a world blessed with something rare in the chaotic realm of red dwarf stars, peace. While most planets orbiting these small, dim stars face relentless barrages of radiation from violent flares, Ross 128b circles a stellar guardian that barely murmurs. Its host star, Ross 128, is a red dwarf so tranquil it's been called the quiet neighbor of our galactic backyard, just 11 light-years away. That serenity could be the key to unlocking this planet's most tantalizing secret, an atmosphere capable of nurturing life. Size matters here. Ross 128b is almost a mirror image of Earth in mass, suggesting a rocky composition with enough gravity to cling to a life-sustaining atmosphere. But what truly sets it apart is location. Nestled snugly in its star's habitable zone, this planet receives only 38% more stellar radiation than Earth, a far gentler embrace than the searing heat bathing most red dwarf worlds. Early climate models paint a picture of a world where temperatures could allow liquid water to flow, provided its atmosphere behaves like a thermal regulator. A modest blanket of greenhouse gases might redistribute heat, preventing the eternal twilight of tidal locking from freezing one hemisphere solid while the other bakes. The absence of stellar tantrums is a game changer. Red dwarfs are notorious for their flares' explosive outbursts that can strip atmospheres and sterilize surfaces in just a few million years. But Ross 128's calm demeanor means its planet might still cling to a protective atmosphere after billions of years, a rarity in such systems. That stability opens the door to something extraordinary: time. On Earth, life took 500 million years to emerge after our planet's formation. Ross 128b has had at least double that span, undisturbed by stellar violence. What might have evolved in such prolonged tranquility? Future telescopes could soon give us answers. The planet's quiet star makes it an ideal target for atmospheric analysis. Unlike flare-prone red dwarfs whose violent outbursts muddy observations, Ross 128's steady glow offers a clean signal. Scientists could scan for water vapor, oxygen, or even methane gases that, in the right combinations, scream life. Imagine detecting an oxygen-rich atmosphere with traces of chlorophyll-like pigments, hinting at alien photosynthesis under a crimson sun. Yet mysteries linger. Is Ross 128b tidally locked, with one face forever turned toward its star, or does it spin just enough to create day-night cycles? The answer could determine whether life blankets the planet or clings to twilight refuges. And what of its geology? Without plate tectonics to recycle carbon, its climate might teeter toward icehouse or hothouse extremes. But if volcanic activity persists, stirring the pot of its chemistry, this world could be far more Earth-like than we dare hope. Ross 128b stands as a testament to cosmic diversity, proof that not all red dwarf planets are hellscapes. It's a reminder that sometimes the most promising worlds aren't the loudest or the brightest, but the quiet ones, humming with possibility just a stone's throw from home. Teagarden's star B defies expectations at every turn, a frozen enigma orbiting one of the smallest, dimmest stars ever discovered. Picture a world where the sun is so feeble it appears as little more than a dull red ember in the sky, casting a twilight glow that barely warms the surface. Average temperatures here likely hover around -60 degrees Fahrenheit, cold enough to flash freeze a human in seconds. Yet beneath this icy shell, something extraordinary might be stirring. Vast subterranean oceans, kept liquid not by sunlight, but by the planet's own internal heat. This tiny world, just 1.05 times Earth's mass, orbits its ultra-cool red dwarf star in a mere 4.9 Earth days, so close that gravitational forces could flex and knead its core like dough. That constant tug of war might generate enough geothermal energy to melt ice deep underground, creating pockets of warmth where life could cling. On Earth, we've found thriving ecosystems in similarly hostile places, bacteria flourishing in Antarctic ice sheets, worms wriggling through deep rock fractures, entire food chains powered by chemical reactions near hydrothermal vents. Teagarden's star B could host its own versions of these extremophiles, organisms adapted to eternal darkness and crushing pressure. The planet's small size adds another layer of intrigue. Unlike gas giants or super-Earths, this is a place where gravity would feel almost familiar, only slightly stronger than home. That means any potential life forms might not need radically different biology to navigate their world. But here's the catch: with such a faint star, photosynthesis as we know it would be impossible. Instead, organisms might rely on chemosynthesis, drawing energy from hydrogen sulfide or methane seeping through the ice. Picture translucent creatures drifting through pitch-black waters, their bodies adapted to harvest geothermal warmth rather than sunlight. What makes Teagarden's star be truly remarkable isn't just its potential for life, it's what it represents. Most exoplanet discoveries focus on larger worlds orbiting brighter stars, but this tiny planet proves that even the faintest, coldest corners of the galaxy might harbor hidden oases. Future missions could scan for indirect signs of subsurface oceans, like minute wobbles in the planet's rotation or traces of water vapor escaping through surface cracks. If confirmed, it would shatter our assumptions about where life can take root. In the end, Teagarden's star B isn't just a scientific curiosity, it's a beacon of cosmic humility. A reminder that life might not need golden sunlight or balmy breezes to flourish. Sometimes all it takes is a little heat from below, a stubborn refusal to freeze, and the quiet persistence of chemistry playing out in the dark. Kepler-22b doesn't just resemble Earth, it haunts our imagination with possibilities, a world so eerily similar to ours that it feels like peering into a cosmic mirror. Located 1,200 light-years away in the constellation Lyra, this distant twin orbits a star cooler and smaller than our Sun, bathing in a gentle orange glow that might give its skies a perpetual sunset hue. What makes this planet extraordinary isn't just its placement in the habitable zone, it's the way it balances on the edge of familiarity and alien wonder. At 1.4 times Earth size, Kepler-22b likely has enough gravity to hold onto a thick atmosphere, yet not so much that it crushes the chance for life as we know it. But here's where the real intrigue begins: water. Models suggest this world could be a global ocean, its entire surface shimmering under that dim sun, with no land masses in sight. Picture endless waves rolling across a planet where hurricanes might span continents, driven by tidal forces from its 367-day year. Yet beneath those turbulent skies, the depths could hold tranquility, layers of water so deep they form exotic ice phases at the bottom, while near the surface, temperatures might hover just right for liquid seas. If life exists here, it wouldn't cling to shores or riverbanks. It would drift, suspended in a planet-wide aquarium, perhaps evolving into vast, floating colonies or organisms that migrate with the currents. The star's calm nature adds another layer of promise. Unlike volatile red dwarfs that bombard their planets with deadly flares, Kepler-22b's Sun is a steady K-type star, offering a stable light source for billions of years. That longevity is key. It's given any potential life forms an unimaginable head start. On Earth, it took roughly 4 billion years for intelligent life to emerge. Kepler-22b has had even longer, its oceans stirring with chemistry uninterrupted by stellar tantrums. Could something in those waters have already crossed the threshold from simple cells to complex, even intelligent beings? Then there's the question of energy. With less sunlight than Earth, organisms might rely on alternative power sources. Hydrothermal vents could dot the ocean floor, spewing minerals that feed chemosynthetic life forms. Or perhaps the planet's thick atmosphere traps heat so efficiently that surface ice remains thin, allowing photosynthetic organisms to thrive in slushy, semi-frozen zones. Some scientists speculate about ice-covered oceans with translucent layers, where microbes harness the faint glow penetrating from above, creating a twilight biosphere unlike anything on Earth. What makes Kepler-22b so compelling isn't just its potential, it's the way it challenges our assumptions. A planet this size shouldn't be so Earth-like, yet here it is, defying expectations. Future telescopes might one day analyze its atmosphere for biosignatures, searching for the faint traces of oxygen or methane that whisper of biology. But even without confirmation, this distant world stands as a monument to cosmic creativity, proving that the ingredients for life aren't rare. They're just waiting to be mixed in ways we're only beginning to imagine. HD 85512b doesn't just push the boundaries of habitability, it dangles right over the edge, a super-Earth clinging to the outer limits of its star's Goldilocks Zone like a mountaineer gripping a sheer cliff face. At 3.6 times Earth's mass, this planet's gravity would turn every step into a workout, pulling down on potential life forms with nearly twice the force we experience. Picture a world where trees grow squat and wide to resist crushing winds, where any creature evolving to move on land would likely resemble a bulldog low to the ground, muscular, built to endure. The mountains here could dwarf Earth's tallest peaks, their jagged summits scraping at an atmosphere thick enough to breathe like syrup, yet paradoxically thin at higher altitudes where the air freezes into glittering CO2 clouds. What makes this world so fascinating isn't just its heft, it's the delicate thermal balancing act it performs. Orbiting an orange dwarf star slightly cooler than our Sun, HD 85512b receives barely enough warmth to keep water liquid, unless its atmosphere steps in as a cosmic insulator. A dense blanket of carbon dioxide, hundreds of times thicker than Earth's, could act like a planetary parka, trapping infrared radiation so efficiently that even the feeble starlight might maintain temperate pockets near the surface. Climate models suggest something remarkable. With the right atmospheric mix, this frosty world could host shallow seas fringed by carbon dioxide snowbanks, their shorelines steaming where geothermal heat seeps through the crust. The chemistry here would be unlike anything on Earth. With so much CO2, the oceans might fizz like soda, their waters saturated with carbonic acid. Yet extremophiles could thrive in these conditions, microbes similar to Earth's acid-loving organisms that flourish in volcanic springs or acidic mine runoff. Photosynthesis, if it exists, might rely on infrared light filtered through that hazy sky, producing alien versions of plants with black or deep purple pigments to absorb every precious photon. And beneath the ice, where geothermal vents spew minerals into the darkness, entire ecosystems could exist independent of the dim sun above. But HD 85512b's most intriguing quality might be its age. At nearly 5.6 billion years old, this planet has had 1 billion more years than Earth to tinker with biology. If life took root here, it's had eternity to adapt to the cold, to the pressure, to the strange chemistry of its carbon-rich world. Imagine organisms with antifreeze proteins coursing through their veins, or creatures that metabolize CO2 directly, breathing what would be poison to us. Future telescopes might detect the faint infrared glow of such a biosphere, or catch whiffs of methane swirling in that dense atmosphere, a gas that shouldn't persist without something replenishing it. This super-Earth challenges every assumption about where life can thrive. It's not the cozy, sun-dappled world we instinctively imagine. It's a place where survival means bending the rules, where biology twists itself to fit extremes. And that's precisely why it captivates us, because if life can cling to existence here, on this frozen ledge of habitability, then the universe might be far more inventive and far more alive than we ever dreamed. Kepler-438b presents a cosmic paradox, a world that checks every box for habitability while orbiting a star that seems determined to snuff out life before it can begin. Picture this, a rocky planet only 12% larger than Earth, basking in the gentle warmth of its star's habitable zone, where temperatures could allow liquid water to pool on its surface. But there's a catch. Kepler-438 Sun is a red dwarf with a temper, unleashing superflares so powerful they dwarf anything our Sun has ever produced. These eruptions blast the planet with radiation levels hundreds of times stronger than Earth's worst solar storms, enough to strip atmospheres and scorch surfaces over time. What makes this world so fascinating isn't just its precarious position, it's the sheer audacity of life's potential there. If organisms exist on Kepler-438b, they wouldn't bask in sunlight or drink from open rivers. They'd likely be subterranean survivors, huddled in labyrinthine caves or buried beneath miles of rock and ice, where the planet's crust acts as a natural radiation shield. Earth offers a glimpse of how this might work. Deep underground, microbes thrive in places like South Africa's Mponeng gold mine, where bacteria live entirely independent of the surface, metabolizing minerals and radioactive decay. On Kepler-438b, similar extremophiles might cluster around geothermal vents, drawing energy from the planet's molten core rather than its hostile sun. The planet's atmosphere hangs in the balance. Early studies suggest it could be clinging to a thin shroud of gases, constantly replenished by volcanic outgassing even as stellar winds try to tear it away. A dense carbon dioxide envelope might help, absorbing radiation while trapping enough heat to maintain liquid water in sheltered pockets. But here's the twist: without a robust magnetic field, something we can't yet confirm, even this protective blanket could be fleeting, leaving the surface exposed to the star's wrath. Yet life, if it persists, would have one advantage: time. Red dwarfs burn for trillions of years, offering eons for adaptation. Imagine organisms with proteins that repair radiation damage in real time, or biofluorescent warning systems that flare when solar storms approach. Their ecosystems might pulse with activity in the brief calm between flares, only to retreat into suspended animation when the next eruption hits. Kepler-438b forces us to rethink resilience. It's a reminder that habitability isn't just about location, it's about endurance. Future telescopes could scan for traces of volcanism or subsurface heat, indirect hints of a biosphere thriving against the odds. Until then, this world stands as a testament to life's stubbornness, whispering that even in the universe's harshest corners, biology might find a way to whisper back. GJ667c isn't just another exoplanet, it's a cosmic chameleon, a world where the very concept of daylight gets rewritten by the dance of three suns. Picture standing on its surface, gazing up at a sky where one star dominates like our sun, while two others glow faintly in the distance, one a dim red ember, the other a pale orange flicker. This isn't a sci-fi fantasy. It's the daily reality for any potential life on this rocky super-Earth, nestled in a triple star system just 22 light-years away. What makes GJ667c so extraordinary isn't just its multiple suns, it's the way their combined light could sculpt climates stranger than anything in our solar system. The primary star, GJ667c, is a red dwarf that bathes the planet in a perpetual crimson hue. But here's where it gets fascinating. The other two stars in the system, though more distant, still contribute their own whispers of warmth and illumination. Their combined gravitational pull creates subtle tidal forces, flexing the planet's crust just enough to potentially fuel volcanic activity or subsurface heating. Imagine a world where seasons aren't dictated by axial tilt alone, but by the shifting positions of these stellar siblings in the sky. Some models suggest GJ667c could experience super seasons, periods where the extra light from its companion stars causes sudden, dramatic thaws, followed by long stretches of cooler stability when the system's alignment leaves the planet reliant on its dim primary star. Then there's the question of daylight itself. With three suns, the planet's day-night cycle becomes a mesmerizing puzzle. Depending on orbital positions, inhabitants might experience double sunrises, where one star crests the horizon just as another sets, or eerie, phantom days, where the secondary stars cast faint, bluish shadows even during the primary star's night. For photosynthetic organisms, this could mean evolving to harness multiple wavelengths of light, red from the dominant star, infrared from the coolest companion, creating alien flora with layered pigments unlike anything on Earth. But the real magic lies in the niches these complex cycles could create. In some regions, the extra starlight might maintain temperate oases where liquid water persists year-round, while others experience sharper contrasts between day and night. Life here wouldn't just adapt to one environment, it would diversify to exploit countless microclimates, from steamy lowlands warmed by all three suns to shaded highlands where only the faintest starlight penetrates. Earth's extremophiles prove life can thrive in everything from acidic hot springs to Antarctic ice. GJ667c's patchwork of conditions could spawn even wilder variations. The planet's dense atmosphere, if it has one, would be the ultimate climate regulator. A thick carbon dioxide shroud could smooth out temperature swings, while high-altitude ice clouds might scatter the faint starlight into a perpetual twilight glow. And beneath the surface, tidal heating from the triple-star gravitational tug of war could maintain vast underground aquifers, shielded from stellar flares and cosmic rays. What makes GJ667c so compelling isn't just its potential for life. It's the way it redefines what a habitable world can look like. This isn't a planet that fits neatly into our Earth-centric models. It's a laboratory for cosmic creativity, where biology could follow paths we've barely imagined. Future telescopes might one day analyze its atmosphere for signs of methane or oxygen, but even without confirmation, this triple-star gem reminds us that the universe doesn't just build planets. It engineers possibilities. Kepler-22b shines as a beacon of cosmic optimism, a world where sunlight doesn't just exist, but strikes the perfect balance between abundance and restraint. Orbiting a star slightly cooler than our Sun, this rocky planet receives about 70% of Earth's solar radiation, placing it in a Goldilocks zone for photosynthesis. Not too dim to freeze its oceans solid, not too bright to boil them away, but just right for the delicate chemistry of life as we know it. Picture a landscape where plants, if they exist, might evolve broader leaves to capture every precious photon, or pigments tuned to the star's orange-tinted light, painting forests in hues of amber and bronze. What sets Kepler-22b apart isn't just its light levels, it's the star's remarkable stability. Unlike the volatile red dwarfs that dominate exoplanet discoveries, this K-type star hums along with minimal flares, offering its planets a rare gift: consistency. Over billions of years, that steadiness could allow atmospheres to persist, climates to stabilize, and life to experiment with complexity uninterrupted by stellar tantrums. Earth's own biosphere took eons to evolve from single-celled organisms to the riot of diversity we see today. On Kepler-442b, that timeline might stretch even longer, giving evolution extra innings to sculpt organisms adapted to its gentler rhythms. The planet's size adds another layer of promise. At 1.3 times Earth's mass, its gravity would feel familiar yet firm, enough to hold onto a substantial atmosphere without crushing potential life under oppressive weight. Models suggest it could host vast shallow seas where sunlight penetrates to the seabed, fueling underwater meadows of algae-like organisms, or perhaps continents straddle its equator, their interiors warmed by geothermal heat, while polar ice caps regulate global temperatures like planetary thermostats. But here's the twist: Kepler-442b's orbit lasts just over 100 Earth days, meaning its seasons, if it has any, would flash by in a blur. Life here might evolve rapid cycles to match, with organisms blooming and retreating in sync with the swift march of its year. Trees could grow fast and lay down dense rings in mere months, while migratory creatures embark on epic journeys across hemispheres multiple times in a single Earth year. The real allure lies in the star's longevity. K-type stars like Kepler-442b's burn for tens of billions of years, far outstripping our Sun's lifespan. If life took root here, it's had more time than Earth to perfect itself, and might persist long after our own star fades. Future telescopes could scan its atmosphere for the telltale signatures of oxygen and chlorophyll, the hallmarks of a biosphere that's not just alive but thriving. Kepler-442b isn't just a scientific target, it's a vision of cosmic patience, a reminder that some worlds aren't just hospitable for a fleeting moment, but for epochs that dwarf human history. In its steady light, we see the possibility of life not as a fragile spark, but as a flame that could outlast the stars themselves. Lighten b isn't just another exoplanet, it's a cosmic neighbor close enough to whisper secrets about alien life, if only we could listen. At just 12 light-years away, this rocky world orbits a dim red dwarf so faint it's invisible to the naked eye from Earth. Yet despite its star's feeble glow, Lighten b might be clinging to something extraordinary, enough warmth to cradle liquid water, thanks to a thick atmosphere acting like a planetary pressure cooker. Picture standing on its surface beneath a perpetual dusk where the sun hangs motionless in the sky, a dull crimson disk no brighter than a full moon on Earth. One hemisphere forever bathed in weak, ruby light, the other lost in eternal night, a world divided between fire and ice. What makes Lighten b so tantalizing isn't just its proximity, it's the way it defies first impressions. Tidally locked planets like this were once written off as hopeless for life, their frozen dark sides and scorching day sides too extreme for anything to survive. But here's the twist. A dense atmosphere could work like a global heating system, ferrying warmth from the sunlit side to the shadowed one through hurricane-force winds. Imagine a planet where storms rage endlessly along the twilight belt, where rain might fall as liquid water on one edge of the Terminator and freeze into snow just miles away. Life here wouldn't need to choose between light and dark. It could thrive in the gradient between, adapting to conditions that shift with every step toward night or day. The chemistry of such a world would be unlike anything on Earth. With so little sunlight, photosynthesis might be impossible, but organisms could evolve to harness geothermal energy seeping through cracks in the crust, or metabolize hydrogen and carbon monoxide swirling in the atmosphere. Deep underground, tidal forces from the star's gravity could keep aquifers liquid, creating hidden oases where microbes flourish far from the harsh surface. And if Lighten B's atmosphere is rich in greenhouse gases like methane or carbon dioxide, it might trap just enough heat to prevent the night side from becoming a solid block of ice, maintaining a slushy frontier where life could cling. But the real magic lies in the planet's stability. Red dwarfs like Lighten's star burn for trillions of years, offering life an unimaginable runway to experiment and evolve. While Earth's biosphere has had a mere 4 billion years to produce intelligence, Lighten B could have had double that or more. Imagine civilizations rising and falling over epochs so vast they dwarf human history, their existence hidden beneath a sky that never changes. Future telescopes might soon glimpse Lighten B's atmosphere, searching for the faint fingerprints of water vapor or methane. Detecting either would transform this nearby world from a scientific curiosity into a prime target for interstellar probes. After all, 12 light-years is practically next door in cosmic terms, close enough that a signal from there, if one existed, would take less than a human lifetime to reach us. Lighten B isn't just a planet, it's a question hanging in the void, waiting for us to answer. Captain B isn't just old, it's a cosmic relic, a planetary survivor with a backstory stranger than fiction. Picture a world born not in our Milky Way, but in a smaller galaxy torn apart by gravitational forces 11 billion years ago, its remains absorbed into our own. This isn't speculation. The planet star, Captain Star, moves backward through our galaxy at breakneck speed, a telltale sign of its extragalactic origins. That means Captain B has witnessed epochs of cosmic history we can scarcely imagine. It was already over 7 billion years old when Earth formed. If life emerged here, it's had triple the time we've had to evolve, adapt, and perhaps transcend biology as we know it. What might 11 billion years of evolution look like? On Earth, life went from single-celled organisms to spacefaring civilizations in just 4 billion years. Captain B's inhabitants, if they exist, could be so advanced they've moved beyond physical forms, existing as pure energy or distributed consciousness woven into the planet's very fabric. Or perhaps they've mastered genetic engineering to the point of immortality, their bodies constantly renewing like cosmic phoenixes. Then again, life here might have taken a different path entirely, organisms evolving to harness the star's faint red light through photosynthesis so efficient it makes Earth's plants seem primitive, or creatures drawing energy from the planet's internal heat in ecosystems sealed beneath miles of rock. The environment itself would be alien to us. Captain's star is a dim red dwarf, bathing the planet in perpetual twilight. Tidally locked with one face forever turned toward its sun, Captain B's dayside might host a narrow band of habitability where temperatures allow liquid water, while the nightside plunges into deep freeze. But after 11 billion years, any life here would have adapted ingeniously, perhaps migrating with the seasons caused by slight orbital wobbles. or building vast underground networks where geothermal vents provide warmth and nutrients. Then there's the question of intelligence. A civilization with billions of years of head start might have technologies indistinguishable from magic stellar engines harnessing their sun's energy, megastructures visible across galaxies, or mastery over spacetime itself. Or they might have chosen a different path, embracing harmony over expansion, their presence undetectable by our crude instruments. The eerie silence of the universe takes on new meaning when considering Captain B. Perhaps advanced life doesn't broadcast its existence, but lives quietly among the ancient stars, watching and waiting. What makes this world so mesmerizing isn't just its age. It's the realization that we might be the newcomers in a galaxy where others have had unimaginable head starts. Future telescopes could scan Captain B for signs of artificial heat signatures or atmospheric pollutants hinting at industry. But even without proof, this ancient traveler challenges our cosmic perspective, whispering that life elsewhere might not just be different, it could be older, wiser, and utterly beyond our comprehension. Kepler-1649c is the exoplanet that almost slipped through the cracks, a world so Earth-like it was hiding in plain sight. When NASA Kepler mission first scanned its patch of sky, the algorithms dismissed it as noise, a blip in the data unworthy of attention. But then, something remarkable happened. A team of researchers decided to double-check the results by hand, scrolling through lines of code like detectives reviewing cold case files. And there it was, a rocky planet, almost exactly Earth-size, orbiting snugly within its star's habitable zone. The discovery sent shockwaves through the astronomy community, not just because of what Kepler-1649c is, but because of what its near misrepresents. If even one planet this promising could evade detection, how many others might still be lurking in the data, waiting for human intuition to spot them? What makes this world so special isn't just its dimensions, it's the way its starlight tells a story of possibility. Kepler-1649c receives about 75% of the sunlight Earth gets from our sun, putting it in a sweet spot where temperatures could allow liquid water to pool on its surface. Its star, a red dwarf, is smaller and cooler than ours, casting a perpetual ruby glow over the landscape. Picture a place where plants, if they exist, might evolve to absorb infrared light, turning entire continents shades of deep purple or black. But here's the twist. This planet's orbit lasts just 19.5 Earth days, meaning its seasons, if it has any, would flicker by in a blur of rapid cycles. Life here would need to adapt to a rhythm far quicker than our own, with organisms possibly evolving accelerated lifespans or hibernation strategies to match the pace. The planet's history adds another layer of intrigue. Red dwarfs are notorious for their violent youth, bombarding planets with radiation in their early years. If Kepler-1649c held onto an atmosphere through that stellar tempest, it could be a testament to the resilience of planetary environments. Some models suggest it might have a thick carbon dioxide envelope, acting like a thermal blanket to retain heat despite the star's faint output. Alternatively, underground oceans could persist beneath an icy crust, shielded from radiation and warmed by geothermal activity. Either scenario opens the door to life, whether floating in algae like mats on the surface or thriving in sunless depths, sustained by chemistry rather than sunlight. Yet the most tantalizing question remains: what else have we missed? Kepler-1649c's discovery proves that even our most advanced algorithms can overlook gems in the cosmic rough. It's a humbling reminder that the search for life isn't just about building better telescopes, it's about pairing them with human curiosity, the kind that pauses to question a line of code or revisit dismissed data. Future missions like the James Webb Space Telescope could soon turn their gaze toward this world, analyzing its atmosphere for hints of water vapor or oxygen. But even without confirmation, Kepler-1649c stands as a beacon of possibility, a testament to the universe's knack for hiding its most precious secrets in plain sight. In the end, this rediscovered world does more than expand our catalogue of exoplanets. It redefines the hunt itself. The next Earth twin might not announce itself with flashing lights or dramatic signals. It might be waiting quietly in the data, overlooked by machines but ready to be found by anyone willing to look closely enough. Kepler-1649c isn't just a planet. It's an invitation to keep searching, to trust our eyes as much as our algorithms, and to remember that sometimes the most important discoveries are the ones we almost didn't make. GJ357d isn't just another frozen world, it's a cosmic paradox, a planet that redefines what habitable can mean in the coldest corners of space. Located 31 light-years away in the constellation Hydra, this super-Earth orbits so far from its dim red dwarf star that its surface temperatures likely plunge to -64 degrees Fahrenheit, cold enough to freeze carbon dioxide solid. At first glance, that makes it seem like a lifeless ice ball, but here's where the story gets fascinating. Beneath that frozen crust, tidal forces and radioactive decay could be churning the planet's interior, creating pockets of liquid water vast enough to rival Earth's largest seas. Picture an alien Antarctica stretched across an entire world, where the ice above is so thick it blocks out all sunlight, yet below, geothermal vents pump heat into pitch-black oceans, creating oases of warmth in the abyss. On Earth, we've found ecosystems thriving under similar extremes, bacteria and tube worms clustering around hydrothermal vents at the bottom of our oceans, surviving entirely without sunlight. GJ357d could host its own versions of these extremophiles, organisms adapted to harness chemical energy rather than light, their biology shaped by pressures that would crush a submarine. What makes this world revolutionary isn't just its hidden heat, it's how its discovery forced scientists to rethink the Goldilocks Zone. Traditionally, the habitable zone was calculated based on surface temperatures allowing liquid water under sunlight. But GJ357d proved that definition was too narrow. A planet doesn't need to bask in a star's warmth to be habitable, it just needs an internal furnace. This revelation flung open the doors to countless icy worlds previously dismissed as sterile moons like Europa and Enceladus, or distant exoplanets like this one, where life might flourish in sunless seas. The planet's dense atmosphere, if it exists, could be the key to preserving these subsurface oceans. A thick shroud of hydrogen or nitrogen might act like a pressure cooker lid, trapping geothermal heat and preventing the oceans from freezing solid over billions of years. Some models even suggest cryovolcanoes, ice geysers erupting from fractures in the crust, could spew nutrients into the ocean below, fueling entire food chains. But GJ357d's greatest gift might be its location. At just 31 light-years away, it's close enough for future telescopes to probe for indirect signs of life. Imagine detecting plumes of water vapor escaping through surface cracks, or chemical imbalances in its atmosphere hinting at subsurface metabolism. These wouldn't be direct proofs, but whispers, tantalizing clues that even in the galaxy's frozen outskirts, the universe finds ways to kindle life. This icy super-Earth challenges us to look beyond the obvious. Habitability isn't just about sunlight and surface lakes, it's about energy in whatever form it takes. Whether from a star's rays or a planet's own fiery heart, life clings where it can, rewriting the rules as it goes. GJ357d isn't just a world, it's a lesson in cosmic creativity, proving that even the coldest places might harbor the warmest possibilities. TOI 1452b doesn't just have water, it's drowning in it. This super-Earth, 100 light-years away in the constellation Draco, isn't just another candidate for habitability. It's a world where the very concept of land might not exist at all. Recent observations reveal something staggering. Up to 30% of its mass could be liquid water, a ratio that makes Earth's oceans look like puddles. Picture a planet where the deepest trenches plunge not 7 miles like our Mariana Trench, but hundreds of miles into an abyss so profound the pressure turns water into exotic forms of ice hotter than lava. What makes TOI 1452b so extraordinary isn't just the volume of water, it's how that water behaves under extreme conditions. At depths unimaginable on Earth, the crushing pressure forces H2O molecules into bizarre configurations like superionic ice, a surreal state where water acts as both solid and liquid, conducting electricity like metal while shimmering with crystalline structure. These alien seas could layer like a cosmic parfait, surface waters churning under the gravitational pull of its nearby star, transitioning through zones of increasing density until reaching a slushy mantle of hot ice wrapped around a rocky core. If life exists here, it wouldn't just swim, it might navigate through labyrinths of floating ice shelves or drift on currents fueled by geothermal vents spewing minerals from the planet's heart. The planet's star adds another layer of intrigue. TOI 1452b orbits a binary system, two dim red dwarfs locked in a slow dance, casting faint ruby light over those endless oceans. With an 11-day year, the planet is close enough to its stars for tidal forces to flex its crust, potentially fueling underwater volcanism. Earth's hydrothermal vents, known as black smokers, host entire ecosystems in complete darkness. On TOI 1452b, such vents might be commonplace, their mineral-rich plumes feeding organisms adapted to harness chemical energy in a sunless world. But here's the real twist. This planet's water content challenges everything we know about how such worlds form. Conventional models suggest super-Earths this close to their stars should be bone dry, their water boiled away by stellar radiation. TOI 1452b's soaked existence implies it might have migrated inward after forming in the icy outskirts of its system, or it's continually replenished by comet impacts. Either scenario makes it a cosmic oddity, a water world thriving where it shouldn't. The search for life here hinges on what's mixed into those oceans. Earth's waters are salted with minerals essential for biology. If TOI 1452b's depths contain similar compounds, dissolved by eons of erosion on its seafloor or delivered by asteroids, its abyss could be a crucible for life stranger than fiction. Imagine organisms with biology tuned to high pressure, their cells reinforced by natural antifreezes, or creatures that communicate through bioluminescent pulses in the eternal dark. Future telescopes could soon glimpse clues. The James Webb Space Telescope might detect water vapor in TOI 1452b's atmosphere, or even hints of methane, a gas often linked to biological activity. But the ultimate answers may require bolder missions, probes capable of penetrating those icy layers, or telescopes sensitive enough to map the faint heat signatures of underwater volcanoes. TOI 1452b isn't just another exoplanet. It's a challenge to our Earth-centric view of habitability, proving that life's true playground might not be rocky continents, but the hidden, endless seas we're only beginning to understand. LP-899c isn't just another exoplanet, it's a cosmic underdog, a world where life might get a second shot at flourishing against all odds. Discovered in 2022, orbiting one of the coolest, smallest stars ever found, this rocky planet defies expectations by sitting comfortably in its star's habitable zone despite receiving barely 1% of the sunlight that bathes Earth. Picture a landscape bathed in perpetual twilight, where the sun hangs in the sky like a dim, rust-colored lantern, casting long shadows across valleys that might cradle liquid water in defiance of the cold. What makes this planet so remarkable isn't just its tenuous grip on warmth. It's the way its star's unusual stability could rewrite the rules for red dwarf habitability. Most small stars like LP-899 are notorious for their violent youth, subjecting nearby planets to radiation bursts capable of stripping atmospheres in just a few million years. But this star is different. Observations reveal it's unusually calm for its type, emitting minimal flares. That tranquility could be the key to LP-899c's survival, giving any potential atmosphere billions of years to persist, evolve, and perhaps even nurture life. The planet's thick atmosphere, if it exists, would be its lifeline. A dense shroud of greenhouse gases like carbon dioxide or methane could act like a planetary pressure cooker, trapping every scrap of heat from the feeble starlight. Climate models suggest even a modest atmosphere might redistribute warmth from the dayside to the nightside, preventing the planet from freezing solid despite its star's faint glow. Imagine a world where slow, syrupy winds carry warmth across the Terminator line, creating a narrow band of temperate conditions where liquid water could pool in sheltered basins or beneath icy crusts. But here's the twist: LP-899c might not be alone. Its system harbors another planet, LP-899b, a scorching hot super-Earth orbiting closer to the star. While this inner world is far too hot for life as we know it, its presence hints at the system's dynamic history. Gravitational interactions between the two planets could have shaped their orbits, perhaps even pushing LP-899c into its current habitable position over billions of years. Alternatively, the inner planet's proximity might have shielded its sibling from the star's early fury, acting as a cosmic buffer that absorbed the worst radiation during the system's turbulent youth. The real magic lies in what we might soon discover. LP-899c's star is so small and cool that the planet blocks a significant fraction of its light during transits, making it one of the best targets for atmospheric study among Earth-sized worlds. Future telescopes could analyze starlight filtering through its skies, hunting for traces of water vapor, oxygen, or even industrial pollutants hinting at advanced civilizations. Detecting any of these would transform our understanding of where life can thrive, proving that even the dimmest stars can cradle vibrant biospheres given the right conditions. Yet the greatest lesson LP-899c teaches us is about cosmic patience. At an estimated 5 to 7 billion years old, this planet has had double Earth's lifespan to experiment with chemistry and just maybe biology. If life exists here, it's had eons to adapt to the slow fade of its star, perhaps evolving organisms that photosynthesize infrared light or draw energy from geothermal vents in the absence of strong sunlight. Its existence whispers that the universe doesn't just create life in ideal conditions, it nurtures it in the quiet, forgotten corners where time and tranquility can work their magic. This unassuming world, hidden in plain sight around one of the galaxy's most common stars, reminds us that habitability isn't about stellar brilliance, it's about balance. A little heat, a little atmosphere, and a lot of time might be all the universe needs to whisper life into being, even in the darkest of places. Kepler-69c began as a beacon of hope, a planet tantalizingly close to Earth size, basking in what appeared to be the perfect orbital sweet spot around its sun-like star. Early observations placed it squarely in the habitable zone, with scientists speculating about balmy oceans and temperate climates. But further study revealed a far more sinister truth. This world might not be a cradle for life, but a cosmic pressure cooker, a Venus in the making with surface temperatures hot enough to melt lead. The revelation transformed Kepler-69c from a potential Earth twin into a cautionary tale, teaching us just how thin the line between habitable and hellish can be. What makes this world so fascinating isn't just its failed promise, it's the brutal physics behind its transformation. Kepler-69c orbits a star 15% less massive than our Sun, but that slight difference in stellar output creates a cascade of consequences. The planet's year lasts just 242 Earth days, meaning it's far closer to its star than Earth is to ours. That proximity, combined with the star's gradual brightening over billions of years, could have triggered a runaway greenhouse effect. Picture an atmosphere so thick with carbon dioxide that sunlight floods in but heat can't escape, turning the planet into a self-heating oven. Oceans that once shimmered under alien skies would have boiled away, their water molecules broken apart by ultraviolet radiation, leaving behind a desolate landscape of cracked salt flats and scorching winds. Yet Kepler-69c's story isn't just about destruction, it's about timing. Venus, Earth's so-called evil twin, likely started with similar conditions: liquid water, moderate temperatures, and the potential for life. But somewhere along the way, their paths diverged catastrophically. Studying Kepler-69c gives us a front-row seat to this process in action, a chance to observe how a planet crosses the point of no return from habitable to hostile. The key might lie in volcanic activity. On Earth, plate tectonics recycle carbon dioxide, regulating our climate over eons. On a planet like Kepler-69c, without this planetary thermostat, volcanic outgassing could have pumped the atmosphere full of greenhouse gases, tipping the balance irreversibly. The implications stretch far beyond one world. Kepler-69c forces us to confront an uncomfortable truth. The habitable zone isn't a guarantee of life, it's just a starting point. A planet's geology, atmospheric composition, and even the temperament of its star play equally crucial roles. Red dwarfs, for instance, might bombard their planets with lethal flares, while sun-like stars like Kepler-69c's could gently simmer their worlds to sterility over billions of years. This understanding reshapes how we search for life elsewhere. Instead of just looking for planets in the Goldilocks Zone, we now scrutinize their atmospheres for signs of runaway greenhouse effects like the telltale fingerprints of sulfuric acid clouds or overwhelming carbon dioxide levels. But here's where the mystery deepens. Some models suggest Kepler-69c might still harbor pockets of habitability, not on its surface, but high in its atmosphere. Venus, despite its crushing heat and acid rains, hosts a narrow band of relatively temperate air 50 kilometers up, where temperatures and pressures resemble Earth's. If Kepler-69c has a similar layer, could airborne microbes or even floating organisms exist there? It's a stretch, but not impossible. Earth's own extremophiles thrive in places we once thought lifeless, from volcanic vents to radioactive waste. Life, if it ever took root on Kepler-69c, might have retreated to this last refuge, clinging to survival in the skies. The real value of Kepler-69c lies in its duality. It's both a warning and a guide, a reminder that habitability is fragile, and a roadmap for identifying other potential Venus-like worlds before we mistake them for paradises. Future telescopes, like the James Webb Space Telescope, could analyze its atmosphere for signs of that irreversible greenhouse tipping point, helping us distinguish true Earth analogs from their toxic doppelgangers. Every new piece of data sharpens our cosmic discernment, teaching us to read the subtle signs that separate a living world from a lifeless one. In the end, Kepler-69 sees legacy isn't about disappointment, it's about nuance. The universe doesn't deal in absolutes, and neither does the search for life. For every planet that meets our hopes, another will defy them, revealing the astonishing diversity of ways a world can thrive or fail. And in that diversity lies the true wonder of exploration, not just finding what we expect, but uncovering the truths we never saw coming. HIP 67522b isn't just another gas giant, it's a cosmic infant, a planetary toddler caught in the act of growing up. At just 17 million years old, this colossal world is younger than some mountain ranges on Earth, giving astronomers an unprecedented window into how planets like Jupiter might have looked in their fiery youth. Unlike the sedate orbits of mature gas giants, this behemoth whips around its star in a blistering 7-day loop, so close that its atmosphere is literally boiling away into space. Imagine a world where the sky isn't just stormy, it's evaporating, creating a comet-like tail of hydrogen gas that stretches thousands of miles into the void. What makes HIP 67522b so revolutionary isn't just its extreme environment, it's the way its violent adolescence challenges our theories of planetary formation. Conventional wisdom said gas giants couldn't form this close to their stars, that they needed to take shape in the cold outer reaches where ices could clump together. Yet here it is, defying expectations. One leading theory suggests this planet might have performed a cosmic migration, spiraling inward from its birthplace beyond the system's frost line. The process would have been chaotic, like a bowling ball plowing through sand, scattering smaller planets out of orbit as it moved. Alternatively, it could have formed right where it is through a process called disk instability, where a dense knot in the protoplanetary disk collapsed directly into a planet, skipping the usual step-by-step growth of smaller rocky cores. The planet's sheer scale boggles the mind. Roughly 10 times Jupiter's mass, its gravity would crush any spacecraft like a soda can, while its atmosphere, a churning soup of hydrogen, helium, and vaporized metals, shimmers at temperatures hot enough to melt iron. Storms the size of solar systems rage across its surface, their winds accelerated by the planet's breakneck rotation. Yet even in this maelstrom, there's beauty. The escaping atmosphere glows under the star's intense radiation, creating an otherworldly aurora that envelops the entire planet in a shimmering veil. Studying HIP 67522b isn't just about understanding one world, it's about rewriting the origin stories of thousands of others. Every observation peels back another layer of mystery. The Hubble Space Telescope has caught hints of water vapor in its stratosphere, a clue that the planet might have formed far enough out to accumulate icy building blocks before migrating inward. Meanwhile, the James Webb Space Telescope's infrared eyes could soon map the planet's temperature variations in unprecedented detail, revealing whether it still glows with the heat of its violent birth. This young giant reminds us that planets aren't static, they're dynamic, evolving entities with life cycles as dramatic as any stars. In a few 100 million years, its star will likely strip away the last of its puffy atmosphere, leaving behind a dense, scorched core. But for now, HIP 67522b burns bright, a cosmic laboratory where the secrets of planetary infancy are written in the swirling gases of its fleeting youth. Wasp 121b isn't just a planet, it's a cosmic inferno, a place where the very laws of chemistry and physics twist into something unrecognizable. Imagine a world so close to its star that its atmosphere reaches temperatures above 4,000 degrees Fahrenheit, hot enough to vaporize iron and tear apart water molecules. Here, the sky doesn't just glow. It screams, radiating a sickly blue hue as titanium and iron gases swirl in the scorching winds. This isn't the gentle shimmer of Earth's auroras. It's the violent incandescence of a planetary furnace, a place where the concept of weather means molten metal condensing into droplets only to evaporate again before hitting the ground. What makes Wasp 121b so mesmerizing isn't just its brutality, it's the way it defies expectations. Most gas giants, like Jupiter, are cold, stormy worlds with layers of ammonia clouds and crushing pressures. But this hot Jupiter orbits its star in a death spiral so tight that a single year lasts just 30 hours. Gravitational forces have stretched the planet into an egg-shaped monstrosity, its outer layers peeling away into space like a cosmic onion being shredded by stellar winds. Telescopes have even detected traces of heavy metals like magnesium and iron high in its atmosphere, elements that should sink into the planet's depths under normal conditions. Yet here they are, suspended in the upper air like glitter in a snow globe, proof of the planet's relentless atmospheric churn. The real horror and beauty lies in its reign. On Earth, water evaporates, forms clouds, and falls back as life-giving showers. On Wasp 121b, the cycle is twisted into something nightmarish. Aluminum and titanium gases rise on the dayside, where temperatures could melt steel, only to be carried by supersonic winds to the marginally cooler nightside. There, these metals condense into liquid droplets, creating storms of molten rain, but the reprieve is brief. Before the droplets can plunge far, they're swept back into the dayside's furnace, vaporized once more in an endless, hellish cycle. Yet for all its violence, Wasp 121b is a goldmine for science. Its extreme conditions act like a laboratory for processes we can't replicate on Earth, showing us how atmospheres behave under stellar bombardment. By studying its light spectra, astronomers have detected water vapor, a shocking find in such a hostile environment where molecules should be ripped apart. This suggests that even in the most unforgiving corners of the universe, the building blocks of life can persist, if only for a fleeting moment. The planet's fate is written in its own skies. With each orbit, it loses more of its atmosphere to space, stripped away by its star's relentless glare. In a few million years, a blink in cosmic time, Wasp 121b may be reduced to a scorched core, a ghost of the giant it once was. But for now, it burns brilliantly, a cautionary tale and a marvel rolled into one. It reminds us that the universe doesn't just create worlds, it engineers extremes, pushing matter and energy to their breaking points just to see what happens. And in that chaos, we find the most extraordinary lessons. 55 Cancri E shatters every fantasy of treasure hunting among the stars. A world where the ground beneath your feet might be worth quadrillions, but the air would melt your lungs before you could take a single breath. Picture a planet twice Earth's size, where mountains aren't made of rock but of compressed diamond, their jagged peaks glittering under the glare of a nearby star. The crust, forged under crushing pressures and searing heat, isn't silicate like Earth's. It's a carbon-rich nightmare, layers of graphite giving way to diamond slabs thicker than continents. If you could somehow mine a chunk of this world, it would dwarf all the gemstones ever unearthed on Earth combined. But here's the cruel twist. 55 Cancri E's riches are locked in a hellscape where the very concept of solid ground is an illusion. Beneath that diamond crust lies an ocean not of water, but of lava, churning at temperatures hot enough to vaporize steel. The planet orbits so close to its sun that a single year lasts just 18 hours, its surface baked to over 4,000 degrees Fahrenheit. Tidal forces have likely locked one face of the planet in perpetual daylight, creating a hemisphere where the lava boils endlessly, while the night side simmers under a cracked crust of cooling diamond. Storms here don't bring rain, they bring waves of molten rock, surging across plains of carbon like some apocalyptic forge. What makes this world a geochemical wonder isn't just its composition, it's the violent processes that sustain it. The star it circles, 55 Cancri A, is richer in carbon than our Sun, seeding the protoplanetary disk with the building blocks for diamond instead of sand. Under normal conditions, carbon might form methane or other volatile compounds, but on 55 Cancri E, the pressures are so intense that carbon atoms snap into crystalline lattices, creating diamonds not through millennia of geological accident, but through planetary-scale violence. Some models suggest the planet's interior could harbor even stranger forms of carbon exotic phases like super diamond, a theoretical material harder than any known substance in the universe. Yet for all its extravagance, 55 Cancri E is a cautionary tale about the limits of habitability. A carbon-rich atmosphere, thick with vaporized graphite and cyanide, would choke any Earth-like life in seconds. The planet's density hints at a core of pure carbon, possibly even a vast sea of liquid diamond swirling around a solid diamond heart. There's no water, no oxygen, just an alchemist's dream turned toxic. But here's the real surprise, 55 Cancri E might not always have been this way. Some astronomers speculate it began as a gas giant, its atmosphere stripped away by stellar winds until only the diamond core remained. Others argue it's the remnant of a cosmic collision, a shattered world reforged in heat and pressure. Either scenario paints a picture of a planet that's lived multiple lives, each more extreme than the last. Future telescopes could unravel these mysteries by analyzing the light filtering through its atmosphere, hunting for traces of carbon monoxide or hydrogen cyanide chemical fingerprints of its infernal chemistry. For now, 55 Cancri E stands as a monument to the universe's capacity for both extravagance and ruthlessness. A world where treasure and terror are one and the same, proving that in the cosmos, even the most dazzling wonders can be utterly, magnificently lethal. HD 189,733b looks like a tranquil blue marble from afar, a soothing azure sphere that could pass for Earth's twin in a cosmic lineup, but zoom in and the illusion shatters. This isn't the gentle blue of oceans and atmosphere. It's the eerie glow of a planet being slowly torn apart, where the sky rains molten glass sideways at speeds that would shred a fighter jet. Winds here don't whisper, they scream across the landscape at 5,400 miles per hour, carrying with them vaporized silicate particles that condense into searing, razor-sharp droplets. Imagine standing on this world, if you could, and witnessing a storm where the precipitation isn't water but liquid shards, hurled horizontally with enough force to strip flesh from bone. What makes this cobalt nightmare so fascinating isn't just its brutality, it's the science behind that deceptive color. The planet's azure hue comes from sunlight scattering through an atmosphere thick with silicate clouds, a phenomenon similar to what gives Earth skies their blue tint. But where our atmosphere filters sunlight gently, HD 189,733b's shroud acts like a cosmic blender, churning those silicate particles into a lethal mist. The temperature swings here are apocalyptic, 2,000 degrees Fahrenheit on the day side, hot enough to melt aluminum, while the night side simmers at a comparatively cool 1,000 degrees. This extreme gradient fuels those supersonic winds as the atmosphere desperately tries to balance the thermal disparity in a frenzy of hyperviolent weather. Yet the real horror lies in the planet's orbit so close to its star that a year lasts just 2.2 Earth days. This proximity triggers tidal forces that stretch and compress the planet's interior, likely fueling volcanic activity beneath that beautiful blue veneer. Some researchers speculate the glass rain might originate in these eruptions, with molten silica spewed into the sky only to be caught in the atmospheric meat grinder. It's a world where geology and meteorology collide in the most vicious way possible, a perpetual cycle of eruption, vaporization, and condensation playing out on a planetary scale. The cruel irony, HD 189,733b, was one of the first exoplanets where scientists detected water vapor in its atmosphere, a discovery that initially sparked hope. But further study revealed the truth. Any water here exists only as steam in a superheated maelstrom, its molecules torn apart by radiation and reassembled in fleeting instants. This world taunts us with the ingredients for life, then demonstrates how easily the universe can twist them into instruments of torture. What makes this planet invaluable to science is precisely its hostility. By studying its extremes, we learn how atmospheres behave under conditions impossible to replicate on Earth. The James Webb Space Telescope has analyzed its light spectra, revealing not just silicates but traces of sodium and hydrogen sulfide, proof that even in hellish environments, complex chemistry persists. These observations refine our models of planetary formation, showing how a world born in similar conditions to Jupiter can evolve into something utterly alien. HD 189,733b's legacy is a lesson in cosmic deception. It reminds us that beauty in the universe often masks unimaginable violence, and that the search for habitable worlds requires looking beyond color and composition to the intricate dance of physics and chemistry that makes a planet truly livable or lethally inhospitable. In the end, this azure monstrosity isn't just a cautionary tale. It's a masterpiece of celestial extremes painted in shades of blue and fury. Ogle 2005 BLG 390 LB doesn't orbit its star. It languishes in the cosmic deep freeze, a world so distant from its dim red dwarf host that temperatures likely plunge to negative 360 degrees Fahrenheit. At nearly 3 times Earth's mass, this frozen super-Earth clings to the outer fringes of its solar system, where its sun appears as little more than a bright star in an endless night sky. But here's where the story takes a fascinating turn. Astronomers suspect this planet might not always have been so isolated. Some models suggest it could have been violently ejected from the inner system during its youth, hurled into the abyss by gravitational chaos, and that's where the possibility of life gets intriguing. Picture a world where the surface is a permanent ice sheet miles thick, its landscape locked in stasis under a sky studded with unfamiliar constellations. Yet beneath that frozen crust, tidal forces or radioactive decay might maintain vast subsurface oceans, insulated from the cold above. We've seen this scenario play out closer to home on Europa, where Jupiter's gravitational pull flexes the Moon's interior, generating enough heat to keep water liquid beneath its icy shell. Ogle 2005 BLG 390 LB could be a scaled-up version of this phenomenon, its massive core churning with geothermal energy that prevents the depths from freezing solid. Hydrothermal vents, like those fueling Earth's deep-sea ecosystems, might dot the ocean floor, spewing minerals into darkness where organisms could metabolize chemicals rather than sunlight. The planet's potential habitability hinges on two contradictory extremes: the crushing cold of its surface and the hidden warmth below. Without an atmosphere to trap heat, its exterior is likely barren, scoured by cosmic radiation and micrometeorites over billions of years. But underground, the rules change. Earth's own extremophiles organisms thriving in polar ice cores or deep within gold mines prove life can persist in isolation, cut off from the surface for eons. On this rogue candidate, any hypothetical life would exist in total darkness, possibly evolving sensory organs tuned to vibrations or chemical gradients rather than light. Their biology might rely on slow metabolic rates to conserve energy in a world where resources are scarce and temperatures hover just above freezing. What makes Ogle 2005b LG 390lb so compelling isn't just its potential for life, it's the way it redefines the boundaries of a habitable zone. Traditionally, we've focused on planets orbiting at just the right distance from their stars. But if worlds like this can maintain liquid water through internal heat alone, the galaxy's real estate for life expands exponentially. Frozen outcasts drifting between stars or distant orbs like this one could outnumber conventional habitable planets by thousands to one. The discovery of this world also raises a profound question. How many other exiled planets might be hiding in the darkness? Current telescopes struggle to detect isolated rogue planets, but future missions like NAS and Nancy Grace Roman Space Telescope could reveal them by the dozens. If even a fraction harbor subsurface oceans, the implications are staggering. Life might not need a sun at all, just a little internal warmth and a lot of time. Ogle 2005b LG 390lb stands as a testament to the universe's quiet ingenuity, a place where life, if it exists, thrives not in spite of the cold, but because of it turning isolation into an evolutionary advantage and darkness into a cradle. PSRB 1257 plus 12b isn't just another exoplanet, it's a cosmic phoenix, a world that cheated death in the most violent way imaginable. Picture a star once like our Sun, swollen in its final days before collapsing in a cataclysmic supernova, an explosion so powerful it outshone entire galaxies. In that maelstrom of energy, any orbiting planet should have been vaporized, reduced to atoms. Yet against all odds, this one survived. Today, it circles the corpse of its progenitor, a pulsar spinning at dizzying speeds, emitting beams of radiation so intense they could strip a human body to the bone in seconds. This is a planet born from apocalypse, bathed in an eternal storm of X-rays and gamma rays, a testament to the universe's capacity for both destruction and stubborn persistence. What makes this world so extraordinary isn't just its survival, it's the sheer improbability of its existence. Pulsars, the ultra-dense remnants of supernova, are stellar zombies, their gravitational fields so strong they warp space-time itself. For a planet to endure the star's death throes and then remain bound to its corpse defies conventional models of planetary formation. One theory suggests PSRB 1257 plus 12b might be a second-generation world, forged from the debris of the supernova itself. Imagine a planet coalescing from the ashes of its predecessor, its very atoms forged in stellar fire. Alternatively, it could have been a gas giant whose outer layers were blasted away, leaving behind a naked core, a diamond-hard relic of what once was. The conditions here are beyond extreme. The pulsar's radiation bathes the planet in a lethal glow, while its magnetic field, trillions of times stronger than Earth's, twists charged particles into spirals of deadly energy. Temperatures swing between scorching heat on the day side and cryogenic cold on the night side, with no atmosphere to soften the extremes. Yet here's the tantalizing question. could life in any form persist in this radioactive hellscape? Earth's own extremophiles offer a clue. Certain bacteria, like Deinococcus radiodurans, can withstand radiation doses thousands of times stronger than what would kill a human. These organisms repair their DNA at astonishing rates, turning survival into an art form. On PSRB 1257 plus 12b, any hypothetical life would need to take this resilience to unimaginable levels, perhaps evolving metallic coatings to deflect radiation, or biochemical pathways that harness the pulsar's energy rather than succumbing to it. The planet's very existence also forces us to rethink the boundaries of habitability. We typically search for life in Goldilocks zones around stable stars, but PSRB 1257 plus 12b proves that biology, if it exists, might flourish in the most unexpected places. Subsurface oceans, shielded by miles of rock and ice, could harbor organisms powered by geothermal vents or radioactive decay. Or perhaps life here would be utterly alien silicon-based, or existing as plasma-like entities dancing in the pulsar's magnetic fields. The possibilities stretch the limits of our imagination. Studying this world isn't just about planetary science, it's about cosmic archaeology. PSRB 1257 plus 12b is a relic of one of the universe's most violent events, a time capsule from a star's final moments. By analyzing its orbit and composition, we piece together the story of its survival. Future telescopes might detect traces of heavy elements in its vicinity, the fingerprints of the supernova that birthed it. Each clue adds to a larger narrative about how planets endure, adapt, and perhaps even give rise to life in the aftermath of destruction. In the end, PSRB 1257 plus 12b isn't just a zombie planet, it's a symbol of defiance. A reminder that even in the face of stellar annihilation, the universe finds ways to preserve its creations. Whether life clings to its irradiated surface or not, this world stands as a monument to resilience, whispering that where there's chaos, there might also be rebirth. TRES-2b isn't just dark, it's a cosmic void, a planet so pitch black it makes fresh asphalt look like a mirror. Imagine standing on its surface, gazing up at a star that bathes your world in light, only for nearly all of it to vanish into an abyss so complete it defies logic. This isn't a trick of perspective or some alien eclipse. TRES-2b, orbiting a star 750 light-years away, holds the record as the darkest known planet in the universe, reflecting less than 1% of the light that touches it. To put that in perspective, coal reflects about 4%. Even black acrylic paint, the darkest substances we've engineered, bounces back more light than this enigmatic world. What makes TRES-2b so baffling isn't just its darkness, it's the way it flips everything we thought we knew about planetary atmospheres. Most gas giants, like Jupiter or Saturn, are relatively reflective, their cloud tops bouncing sunlight back into space with ease. But TRES-2b, a hot Jupiter searing under its star's relentless glare, behaves like a cosmic sponge, absorbing almost every photon that dares to strike it. The leading theory, its atmosphere might be laced with vaporized sodium and potassium, elements that greedily swallow visible light. But here's the twist, these chemicals alone shouldn't create such profound blackness. Some researchers speculate the planet's upper atmosphere could be shrouded in exotic, light-absorbing molecules we've yet to identify, a haze of titanium oxide or even clouds of carbon particles, turning its skies into a perpetual, starless midnight. The planet's scorching temperature adds another layer of mystery. At nearly 2,000 degrees Fahrenheit, it's hot enough to glow a faint, hellish red, like embers in a forge. Yet instead of radiating that heat as visible light, TRES-2b seems to vanish into the background, its thermal energy escaping as infrared invisible to our eyes. This paradox makes it a nightmare to study. Even the most advanced telescopes struggle to distinguish it from the void of space, its presence betrayed only by the slight dimming of its star as it transits. But the real enigma lies in its origin. How does a planet become this dark? One possibility is that TRES-2b's atmosphere lacks the reflective cloud decks found on other gas giants, leaving only those light-devouring gases exposed. Alternatively, its proximity to its star, so close that a year lasts just 49 hours, might have stripped away any reflective layers, leaving behind a naked, soot-stained core. There's even a chance its atmosphere is so hot that molecules break apart into atoms, creating a plasma-like shroud that absorbs light with terrifying efficiency. The implications stretch far beyond one world. If planets like TRES-2b are more common than we thought, our models of planetary formation might need rewriting. Dark, lightless worlds could be lurking in the shadows of countless star systems, invisible to our current detection methods. And if life exists in such places, it would have evolved in an environment where the very concept of day is meaningless, where photosynthesis is impossible, and where survival depends on harnessing heat or chemical energy from the planet's interior. TRES-2b's darkness isn't just a curiosity, it's a challenge. A reminder that even in a universe flooded with starlight, some worlds choose to wear the night like a cloak, hiding their secrets in plain sight. Future telescopes, equipped with infrared and spectrographic tools, might one day peel back that veil, revealing what truly lurks in the heart of the darkest planet we've ever known. Until then, it remains a cosmic riddle, whispering that sometimes the most profound mysteries aren't just about what we can see, but what we can't. Wasp-12b isn't just dying, it's being devoured in real time, a planet caught in the cosmic equivalent of a python's grip, slowly squeezed and stripped apart by its own star. Every second, this gas giant loses over 6 billion tons of atmosphere, ripped away by gravitational forces so intense they've stretched the planet into an egg-shaped wreck. At just 4 million years old in cosmic terms, Wasp-12b should be in its planetary prime. Instead, it's on borrowed time, with maybe 3 million years left before its star finishes the feast, leaving behind nothing but a stripped core. The horror unfolds in the details. Wasp-12b orbits so close to its yellow dwarf star that a single year lasts just 26 hours, its dayside broiling at 4,000 degrees Fahrenheit, hot enough to vaporize titanium. That proximity triggers tidal forces 100,000 times stronger than the moon's pull on Earth, distorting the planet's very structure. Imagine a world where the ground beneath your feet isn't solid but a seething, superheated gas, stretched and compressed until it bleeds into space. The star's gravity doesn't just pull, it peels, creating a comet-like tail of stolen atmosphere that stretches over 2 million miles into the void. Telescopes have caught this grisly spectacle in action, watching as hydrogen, helium, and even complex molecules like carbon monoxide are torn from the planet's grip. Yet within this destruction lies an eerie beauty. The stolen gases don't just vanish, they spiral into a glowing disk around the star, a temporary cosmic tattoo marking where the planet once thrived. Some of this material might even rain back down onto Wasp-12b's night side, creating a macabre cycle of evaporation and condensation. The planet's upper atmosphere, meanwhile, has become a chemical factory. Under the star's relentless ultraviolet assault, molecules break apart and recombine into exotic compounds rarely seen elsewhere, including hydrocarbons that could coat the remaining gases in a sooty haze. Here's the chilling parallel. Wasp-12b's fate mirrors what awaits Earth in about 5 billion years when our Sun swells into a red giant. Mercury and Venus will be consumed entirely, while Earth's oceans will boil away, its crust melt, and its atmosphere evaporate into the void. Wasp-12b is giving us a front-row seat to this process, compressed into a timescale humans can almost comprehend. It's a reminder that planetary death isn't always sudden. Sometimes it's a slow, inevitable unraveling, where gravity plays the role of both architect and executioner. But the real lesson of Wasp-12b isn't just about endings, it's about legacy. The carbon-rich material bleeding from this world could seed future planets or even become part of new life elsewhere. In a twist of cosmic irony, the very elements being torn away might one day help build something new. For now, though, this doomed giant burns bright against the dark, a fleeting masterpiece of destruction that teaches us how the universe reclaims its own. HATP-7b isn't just another hot Jupiter. It's a cosmic jewelry box, a world where the skies might rain gemstones. Imagine standing on this scorching giant, gazing up at clouds that don't just drift but glitter, their crystalline structures catching the light of a star so close it fills half the sky. These aren't water droplets or even sulfuric acid like Venus toxic shroud. They're likely made of corundum, the same mineral that forms rubies and sapphires back on Earth. At temperatures soaring above 4,000 degrees Fahrenheit, aluminum and oxygen atoms in the upper atmosphere could bond into these exquisite crystals, creating a celestial spectacle unlike anything in our solar system. The planet's eternal day side is where the magic happens. Here, the savage heat vaporizes minerals that would remain solid on cooler worlds, lifting them high into the atmosphere where they condense into gemstone clouds. Some models suggest these corundum particles might grow large enough to actually precipitate not as rain, but as microscopic gem dust swirling in violent winds that exceed 500 miles per hour. The night side tells a different story. As temperatures plunge by nearly 1,000 degrees, these same clouds could solidify into vast floating lattices, creating a shimmering haze that reflects the star's light like a disco ball made of crushed sapphires. What makes HATP-7b truly mesmerizing is how its atmosphere dances between extremes. The same brutal conditions that create these gem clouds also tear them apart. Ultraviolet radiation from the star bombards the planet, potentially breaking down some crystals while simultaneously forging new ones in a relentless cycle of creation and destruction. This isn't a static jewel. It's a dynamic, ever-changing masterpiece where cloud formations might appear and vanish within hours, their fleeting beauty dictated by the planet's vicious weather patterns. The planet's composition adds another layer of wonder. Unlike most gas giants dominated by hydrogen and helium, HATP-7b shows signs of being enriched with heavier elements, the building blocks of those precious mineral clouds. This suggests it might have formed farther out in its system, where ices and silicates were more abundant before migrating inward to its current hellish orbit. Along the way, it could have swallowed rocky debris, accumulating the raw materials that now sparkle in its skies. Yet for all their beauty, these gemstone clouds are utterly hostile to life as we know it. The corundum particles would be razor-sharp, their edges capable of shredding organic molecules to ribbons. Any spacecraft venturing into those glittering skies would find itself sandblasted by a storm of microscopic jewels, its hull pitted and scored by the very beauty it came to study. Future telescopes might soon glimpse this spectacle directly. By analyzing how light filters through HATP-7b's atmosphere during transits, astronomers could detect the telltale signatures of aluminum oxide, the chemical fingerprint of those celestial gemstones. If confirmed, it would transform our understanding of planetary atmospheres, proving that the universe doesn't just create worlds, it ornaments them with nature's most exquisite treasures. HATP 7b stands as a reminder that cosmic splendor comes in many forms. From diamond planets to sapphire clouds, the galaxy continually reinvents what's possible, blending the familiar with the fantastical. These glittering skies may be out of reach, but their existence sparks something precious in us, the realization that even in the harshest corners of space, nature still finds ways to take our breath away. Kelt 9b isn't just hot, it's a cosmic furnace, a world where the very laws of chemistry unravel under temperatures so extreme they rival the surface of some stars. Daytime here soars to a staggering 7,800 degrees Fahrenheit, hotter than the melting point of steel and even some red dwarf stars. This isn't a planet where molecules cling together. It's a realm of raw, dissociated atoms, a place where hydrogen gas doesn't exist as H2, but as solitary protons and electrons whipping through a superheated haze. If you could stand on its scorched surface, not that you'd survive the attempt, you'd witness a sky perpetually ablaze, the air itself ionized into a searing plasma that glows like the inside of a fusion reactor. What makes Kelt 9b so fascinating isn't just its heat, it's the way it defies the very definition of a planet. Orbiting a blue-white star twice as hot as our Sun, this gas giant is stretched into an oblong shape by tidal forces, its atmosphere bleeding into space like smoke from a candle. The star bombards it with ultraviolet radiation so intense that the planet's outer layers are literally boiling away, leaving behind a comet-like tail of vaporized metal and gas. Iron, titanium, and even silica don't stand a chance here. They exist only as vapors, their atoms too energetic to bond into the minerals we know on cooler worlds. Yet within this atomic chaos lies a scientific goldmine. Kelt 9b is a natural laboratory for studying matter under conditions impossible to replicate on Earth. Here, astronomers have detected traces of ionized iron and titanium in the upper atmosphere, atoms so excited by the heat that they emit light at specific wavelengths, painting the planet's spectral signature with the colors of a cosmic forge. These observations offer clues about how materials behave at energy levels usually seen only in particle accelerators or the cores of stars. It's as if the universe has handed us a Petri dish for extreme physics, a place where we can observe the behavior of matter at its most fundamental level. The planet's orbit adds another layer of drama. A single year on Kelt 9b lasts just 36 hours, its path so close to the star that the gravitational forces have likely locked one hemisphere in perpetual daylight, while the other faces the void of space. But don't be fooled, the night side is no refuge. Even there, temperatures hover around 4,000 degrees, hot enough to melt tungsten. The sheer violence of this environment means Kelt 9b won't last forever. Current estimates suggest it's losing about 10 billion tons of atmosphere every second, a rate that could strip it bare within a few 100 million years. What remains when a planet like this dies? Some theories suggest it might leave behind a bare, rocky core, a cinder of what once was, glowing faintly in the ashes of its own evaporation. Others speculate it could vanish entirely, its material scattered into the stellar wind, destined to be recycled into future generations of stars and planets. For now, though, Kelt 9b burns brightly, a testament to the universe's capacity for extremes. It challenges our assumptions, proving that planets can exist in realms we once thought reserved for stars alone, and in doing so, it expands our understanding of what's possible in the cosmos. GJ 504b shatters every expectation of what a planet should look like, a world painted in hues that seem ripped from a fantasy novel rather than the cold darkness of space. Imagine a gas giant glowing with an ethereal magenta hue, its atmosphere radiating warmth like a cosmic ember against the void. This isn't the familiar tan of Jupiter or the icy blue of Neptune. It's a vivid pink sphere, a celestial anomaly that reminds us the universe's palette extends far beyond our solar system's muted tones. What makes this world so visually striking isn't just its color. It's the story behind that rosy glow. At just 160 million years old, GJ504b is a planetary infant, still burning with the residual heat of its violent birth. Unlike the cold, settled gas giants of our solar system, this young world radiates its own energy, emitting infrared light that tints its cloud tops in shades of cherry blossom and coral. The exact chemistry behind this spectacle remains debated, but astronomers suspect the planet's upper atmosphere might be rich in exotic compounds like ammonia or phosphine, scattering light in ways that transform its appearance into something otherworldly. The planet's isolation adds another layer of intrigue. Orbiting 59 times farther from its star than Earth does from the Sun, GJ504b drifts in a realm where sunlight is feeble at best. Yet instead of freezing into obscurity, it shines with its own inner fire, a testament to the raw energy unleashed during planetary formation. The gravitational collapse that birthed this world left it simmering at temperatures around 460 degrees Fahrenheit, hot enough to glow in visible light, but not so hot that it drowns out that distinctive pink. But GJ504b isn't just a pretty cosmic oddity. It's a challenge to our theories of planetary formation. At 4 times Jupiter's mass, it defies conventional models that say gas giants can't form so far from their stars. Some astronomers argue it might have been born closer in and violently ejected, while others propose it assembled directly from a gravitational instability in the protoplanetary disk. Either scenario forces us to reconsider how planetary systems evolve, especially around stars like GJ504, a sun-like star quietly hosting a rebel world on its fringes. The discovery of this pink giant also hints at unseen diversity. If one young planet can glow magenta, what other colors might be hiding in the cosmos? Could there be cobalt worlds with cobalt clouds or emerald planets tinted by exotic atmospheric chemistry? GJ504b proves that planets aren't bound by the muted shades of our solar system. They can be as vibrant as any artist's imagination. Future telescopes might reveal even wilder spectacles, from ultraviolet gas giants to planets striped like cosmic candy. For now, GJ504b stands as a reminder that the universe delights in surprise. A world where the familiar rules of color and composition don't apply, where heat and chemistry conspire to create something breathtakingly beautiful. It's not just a planet, it's a masterpiece painted in light and time. The next decade of exoplanet exploration isn't just about finding more worlds, it's about unraveling their deepest secrets with technology so advanced it borders on science fiction. The James Webb Space Telescope, already revolutionizing our view of the cosmos, acts like a universal chemist, dissecting starlight filtered through distant atmospheres to identify molecules we once thought undetectable across light years. But Webb is only the beginning. The extremely large telescope, rising from Chile's Atacama Desert with a mirror nearly the size of a blue whale, will capture direct images of exoplanets so sharp we might see cloud patterns swirling in their skies. These instruments don't just observe, they interrogate, searching for atmospheric fingerprints like oxygen and methane that shouldn't exist together without biological activity. Imagine analyzing the air of a planet 40 light-years away and spotting the telltale dip in a light spectrum that screams forests or oceans. That's the precision these telescopes offer. Methane, which breaks down quickly in most atmospheres unless replenished. Oxygen, which reacts violently with rocks unless continuously produced. Together, they form a chemical signature that, on Earth, means only one thing: life. But the hunt goes beyond these familiar clues. Scientists are now compiling a cosmic database of biosignature cocktails, unexpected combinations like nitrous oxide paired with chloromethane, gases that might indicate alien metabolisms functioning in ways we've never imagined. The real game changer lies in temporal observations. Instead of single snapshots, next-generation telescopes will monitor exoplanet atmospheres over months or years, watching for seasonal changes in gas concentrations. A sudden spike in oxygen during a planet's summer could reveal photosynthetic cycles, while fluctuating methane levels might hint at microbial activity responding to temperature shifts. Some teams are even developing algorithms to detect artificial pollutants like nitrogen dioxide technosignatures that would imply not just life, but intelligence capable of altering its environment. Yet the greatest discovery might come from where we least expect it. The TRAPPIST-1 system, with its 7 Earth-sized worlds, remains a prime target, but surprises often lurk in overlooked corners. A frozen super-Earth like GJ357d could harbor subsurface biosignatures venting through cryovolcanoes, while a tidally locked planet like LHS 1140b might concentrate atmospheric clues along its twilight zone. Even failed stars called brown dwarfs, too small to ignite fusion, could host floating microbes in their relatively temperate upper atmospheres, a concept that expands the habitable zone beyond traditional boundaries. What makes this era unprecedented isn't just the technology, it's the statistical certainty. With thousands of confirmed exoplanets and billions more likely waiting, the numbers suggest that life's ingredients are universal. The real question isn't if we'll find evidence of biology beyond Earth, but when and how profoundly it will reshape our understanding of existence. When that moment comes, it won't be a single headline, it'll be a cascade of data, a chorus of spectral lines whispering across the cosmos, telling us we were never alone in the first place. The universe teems with possibilities. 40 enigmatic exoplanets alone could harbor life, with billions more waiting beyond, yet the cosmos remains eerily silent. This is the Fermi Paradox in full force. If the conditions for life are so abundant, where is everybody? The contradiction between high probability and zero evidence gnaws at our understanding of existence. One explanation cuts deepest. Perhaps life isn't just rare, but vanishingly so. Even on worlds with liquid water and stable climates, the leap from chemistry to biology might require such precise conditions that Earth's thriving biosphere is a cosmic fluke. Imagine a galaxy where thousands of planets have the right ingredients, but only one ours ever stirs them together correctly. But there's another, darker possibility. Civilizations might arise frequently, only to snuff themselves out before they can signal the stars. Nuclear war, climate collapse, or runaway AI could act as universal filters, culling intelligent life at critical thresholds. If this great filter lies ahead of us rather than behind, humanity's future could be bleaker than we dare admit. Alternatively, advanced societies might choose silence. They could be out there watching and waiting, deliberately avoiding contact to steer clear of chaos, or to observe us like some interstellar nature preserve. Then there's the technological blind spot. Our search for extraterrestrials assumes they communicate as we do: radio waves, optical signals, or megastructures like Dyson spheres. But what if they've moved beyond these crude methods? A civilization just 1,000 years ahead of us might use neutrino messaging, quantum entanglement, or something we can't yet conceive. We could be surrounded by conversations, all humming in frequencies we're biologically and technologically unequipped to notice. The paradox also challenges our perception of time. The universe is 13.8 billion years old, plenty of epochs for civilizations to rise and fall before Earth even formed. Entire galactic empires might have flourished and faded, leaving behind ruins too distant or decayed for us to detect. Or perhaps we're among the first, with the bulk of intelligent life still waiting for the right cosmic moment to emerge. Ultimately, the silence isn't just a scientific puzzle. It's a mirror. Every possible answer forces us to confront our own fragility, our assumptions, and our place in the story of the cosmos. Whether we're alone, being ignored, or simply unable to hear the chorus, the universe keeps its secrets close. And that, perhaps, is the most profound lesson of all. The search for exoplanets isn't just for astronomers in observatories. It's happening right now on laptops and tablets around the world, and yours could be next. Imagine scrolling through telescope data with your morning coffee and spotting the faint, rhythmic dip of a star's brightness that signals an undiscovered world. This isn't science fiction, it's the reality of citizen science projects like Planet Hunters, where volunteers have already helped identify over 100 potential exoplanets missed by algorithms. These discoveries don't require advanced degrees or expensive equipment, just curiosity and a willingness to learn. What makes these initiatives so revolutionary is how they democratize discovery. Professional astronomers are drowning in data. Missions like TESS and Kepler generate more light curves than any research team could analyze alone. That's where the global community steps in. The human eye excels at pattern recognition, often catching subtle anomalies that even sophisticated software overlooks. Take the case of KIC 8,462,852. Better known as Tabby's star, whose bizarre flickering behavior was first flagged by citizen scientists. Their observations sparked years of research into potential alien megastructures, proving that amateurs can propel science forward in unexpected ways. Getting involved is easier than you might think. Platforms like Zooniverse offer intuitive tutorials that transform complex data into engaging puzzles. You'll start by reviewing light curves graphs showing a star's brightness over time and flagging anything unusual. Some dips are planetary transits, others stellar flares or instrument glitches, but each click contributes to training AI systems to improve future searches. The thrill comes when your flagged data gets reviewed by professional astronomers, potentially leading to your name in a scientific paper. Over 50 volunteers have already earned co-author credits this way, their contributions immortalized alongside PhDs in peer-reviewed journals. Beyond exoplanets, the universe offers endless opportunities for hands-on exploration. Projects like Backyard Worlds hunt for brown dwarfs at the edges of our solar system, while Galaxy Zoo classifies distant galaxies based on their shapes. There's even SETI Live, where participants analyze radio signals for potential extraterrestrial communications. The common thread: every click advances real science, turning screen time into a cosmic treasure hunt. The tools are evolving too. New apps like Exoplanet Watch guide users through processing their own observations using backyard telescopes, while machine learning courses designed for citizen scientists make it possible to contribute to cutting-edge research. Imagine combining these skills, your sharpened intuition for patterns with AI's computational power, to sift through data at unprecedented scales. The next breakthrough might not come from a mountaintop observatory, but from a kitchen table in Kansas or a dorm room in Nairobi. This isn't just about finding planets, it's about rewriting the story of who gets to be a discoverer. When a retired teacher in Ontario or a high school student in Brazil helps identify a distant world, they prove that science isn't an exclusive club. The cosmos belongs to everyone, and with each new pair of eyes joining the search, we expand not just our catalogue of exoplanets, but our collective sense of wonder. So why watch from the sidelines when you could be part of the greatest exploration in human history? The data is waiting, the tools are free, and the next world to be found might just have your name on it. From molten hellscapes where the skies rain glass to frozen worlds hiding oceans beneath miles of ice, these 40 exoplanets have rewritten the rules of what life might endure. We've wandered through diamond-studded deserts, danced in the twilight of tidally locked paradises, and plunged into the abyss of water worlds deeper than our wildest dreams. Yet for all their diversity, they share one profound truth. Each one is a laboratory, testing the limits of biology against the backdrop of an indifferent universe. The absence of definitive proof doesn't mean we're alone. It means we're just beginning to listen. Our tools are evolving from crude telescopes to molecular sleuths capable of sniffing out biosignatures across light years. What was once speculation is now a matter of precision. The next decade could deliver the faint but unmistakable signal of oxygen in an exoplanet's atmosphere, or the chemical whisper of chlorophyll under an alien sun. The hunt has shifted from if to when, and every discovery tightens the net. But the real revelation isn't just about finding life, it's about redefining what life even means. A microbe surviving in the sulfuric clouds of Venus would be as groundbreaking as an intelligent civilization beaming signals our way. The universe doesn't owe us familiar answers. It might offer something stranger, silicon-based organisms thriving in methane lakes, or electromagnetic entities pulsing in the plasma winds of a dying star. The more we explore, the more we realize that alien isn't just a description, it's a spectrum, vast and uncharted. So keep watching the skies, but not just with telescopes, with imagination. The greatest discoveries often come from those willing to question assumptions, to entertain the improbable. That's how we found planets orbiting pulsars, how we realized rogue worlds drift between stars, how we learned that habitable is a canvas, not a checklist. The day we confirm we're not alone won't be an ending. It'll be a beginning, a cosmic handshake that launches a new chapter in humanity's story. Until then, the silence isn't empty. It's full of possibilities, each exoplanet a riddle waiting to be solved. And whether the answer comes tomorrow or a century from now, one thing is certain: the universe has been hiding its secrets for billions of years. It's only a matter of time before it starts whispering them